good morning to everyone present here. On behalf of IIT Guwahati, I warmly welcome you all to the inaugural ceremony of the GIAN course on analysis of the impact of wind power plants on radar system. To share the vision and objectives of this course, I now invite Professor Ashwini Sawant, our host faculty, to address the gathering.
Good morning everyone. I welcome you all. I, Dr. Ashwini Sawant, Assistant Professor in Electronics and Electrical Department, IIT Guwahati, also the co-host of this GIAN course on the analysis of the impact of the wind power plants to the radar system, organized by the Center of Education Technology and Department of Electronics and Electrical Engineering, IIT Guwahati, spanning from 1st December to 5th December 2025. I welcome you all. I welcome all the faculty members, all the researchers, academicians, and the industry professionals who are present here to attend this course. Looking all of you who are present physically as well as virtually. It's a great motivation for all of us. I also would like to welcome our guest. So I am deeply honored to have with us Professor Hemant B. Kaushik, Dean of Online Education and Skilling, IIT Guwahati. Your presence actually give a very much higher significance to this inauguration ceremony of this event, sir. I also like to welcome Professor Harshal B. Nimade, the head of the Department of Electronics and Electrical Engineering. Also Dr. Salil Kashyap, coordinator of Center of Education and Technology. Sir, thank you for joining us here. I also thank and welcome my colleague, Professor Gaurav Trivedi, who is also the co-host of this GIAN course. Thank you for starting this initiative and giving wonderful contribution to actually design and curate this course for all the different or kind of audiences who are present here. And in the last, I would also like to thank our foreign expert, Professor GIAN Pidanic from University of Pardubice. Thank you, Jan, actually, for joining us joining hands with with Gaurav sir and me to design this GIAN course. So we are looking forward that you will have will be giving and sharing the lot of knowledge regarding this GIAN course to all the audiences who are present here. If I discuss about the registration, so we have received a lot of positive response from all of you. We have received a number of registration requests from the students, from the academia partner, industry professionals and researchers. Even I have witnessed that few students has been coming from the various part of the country to join this course physically. So this is a really boost for us. And I hope that you all will be engaged in a wonderful technical discussions over this course of 5 days. If I give you a little bit introduction about this course, so as we know that globally these days we are more pushing towards the green and sustainable energy solutions, especially the wind power energy is also the one of the greatest solutions that comes into the mind. And India is also not looking behind to that. India is also contributing in that way. If I share you some statistics, in up to 2025, the power energy, the capacity of the electrical generation is reached up to the 51 gigawatt in India especially. And in the last fiscal year 2024 to 25, the rise in this capacity is up to the 4 gigawatt, which is almost around 8%. So it means that the government is pushing towards installing more and more wind power mills and wind power plants. So this installation is actually enhancing the capacity of our country towards the green energy and sustainable energy solutions. But on the other hand, these solutions are also impacting the radar system, existing radar systems. So we should be more careful when we are studying the interaction of the scattering that is coming out of this wind power mills to the radar system, existing radar system, which is also very crucial for the our defense system, for the air traffic control and the weather predictions and all. So this course will actually trying to analysis that impact the wind power means the impact on the existing radar system. So I will just rest here. I will give more opportunity to Professor GIAN to discuss more that into the detail later on. So with this, I will just in the end I will just like to welcome you all again, and hope that these next 4 to 5 days will be much more technically enriching for all of you, and you will gain a lot of knowledge from here. Thank you very much.
Thank you very much, sir, for sharing valuable insights and for wonderfully presenting the vision of this course. To offer more insights and remarks, I warmly invite Professor Gaurav Trivedi, host faculty of this course, to the stage.
A very good morning to all the participants, my colleagues who are here on the dais, and those who are here precisely from the CET. Dr. Ashwini has already set up the pitch, so I need not to add more, but I just welcome all of you, and I believe that this course will really impart the vital knowledge, okay, and which is precisely in the radar system and the impact of windmills and all, because Dr. GIAN, who is a well-known expert in this area, and he comes from a place in Pardubice, Czech Republic, which hosts a number of manufacturing corporations. And his association with the industry and the real hands-on project has given him the edge and the knowledge which is unparalleled. So with this, a new beginning to the new learning to all of you. I hope that all of you will enjoy. So once again, I welcome to the course and welcome to the guests who are here. Thank you.
Thank you very much, sir, for your valuable remarks. Now I would like to invite Professor Salil Kashyap, coordinator of the Center for Educational Technology, to the stage.
Dean Online Education, Professor Hemant Kaushik, Head of the Electronics and Electrical Engineering Department, Professor Nemade, the foreign expert, Professor Jan Pidanic from the University of Pardubice, Czech Republic, the co-hosts, Dr. Ashwini Sawant and Professor Gaurav Trivedi, participants. Good morning, everyone. So on behalf of the organizing team at the Center for Educational Technology, IIT Guwahati, it is my privilege and honor to welcome you to this inaugural ceremony of the GIAN course. As you all know, GIAN is so GIAN, also known as the Global Academy Initiative of Global Initiative Academy Networks. This is an initiative of the Ministry of Education, Government of India, to sort of foster academic collaboration between Indian and international faculty, so that this takes the shape of an academic network, and you sort of get a flavor for international research. Talking about the center, CET is an interdisciplinary center at IIT Guwahati, which has been involved in several mission projects of national importance, such as NPTEL MOOCs, GIAN, TechIP. It also offers defense training courses, training for executives of Bharat Electronics Limited, just to name a few. Some other projects focused specifically to the northeastern region. Yeah, so so with this, I would like to welcome all participants, and I wish that over the next 5 days, you have a truly engaging and interactive session with the experts, both Indian and the foreign expert, and wish you happy learning. Thank you.
Thank you, sir, for your thoughtful address and for your support. With great respect, I invite Professor Harshal B. Nemade, Head of the EEE Department, IIT Guwahati, to the stage.
Distinguished guests and speakers, of this GIAN program, my colleagues and dear participants. I welcome you all on behalf of the Department of Electronics and Electrical Engineering to this GIAN course on a unique topic that probably we would not have heard of 20 years ago. But then you are fortunate that you have the expert in person with you, and this is a good opportunity for you, and I wish you make most of this opportunity. I also hope that these 5 days will be full of knowledge and interaction, and that to some of you while you enjoy staying at IIT Guwahati campus. So good luck and best wishes. Thank you.
Thank you, sir, for your inspiring words and for taking the time to be with us today. I welcome to this stage Professor Hemant B. Kaushik, Dean of Online Education and Skilling, to kindly come forward and share thoughts with us.
Thank you. A very good morning to you all. IIT Guwahati takes immense pleasure to welcome everyone, all the participants who are visiting IIT Guwahati as well as all those who are online. Welcome to IIT Guwahati. To begin, let me thank Dr. Ashwini, Dr. Gaurav to think about this very unique program which Professor Nemade has already said that we could not have thought about it few years back. So it's a very specialized program, and this is the beauty of GIAN programs. If you look all these programs, you will find some specialized unique programs are being offered throughout the country every year. So special thanks to our expert Professor GIAN from Czech Republic, who agreed to visit us and interact with you. Like Professor Salil said, that GIAN means Global Initiative for Academic Networks. So don't forget the last word, which is networking, collaboration. So just don't think that this is a classroom kind of teaching and you are just here to listen and then go back. Use this time, use this opportunity to develop your network with IIT Guwahati, different departments. We have 25 centers and departments and schools here who work in different areas. You also try to develop collaboration and networking with our foreign expert, with different faculty members who are working in different areas at IIT Guwahati. CET is one unique center in IIT Guwahati which offers large number of skilling programs. Now some of these skilling programs are very unique, some of these skilling programs are very general in nature. So we offer more than 100 courses on NPTEL every year. So this is a big number. NPTEL, I hope you know that these courses are available freely to everybody, but if you want a certificate, there is an examination with a little bit of fee. In addition to these skilling programs, IIT Guwahati offers very popular online degree program, which is 100% online. So one undergraduate degree program is BSc Honours in Data Science and Artificial Intelligence. And currently there are about 3,200 students enrolled in this single degree program. Right, so that's about 1/3 or more than 1/3 of the entire population, student population of IIT Guwahati. We have around 8,500 students, and this single degree has more than 3,000 students. This is very popular, and why it has become popular is because of the huge flexibility that it offers. So you can choose the number of courses you want to study, you can choose which course you want to study or don't want to study in a particular trimester depending on your other schedule. The flexibility in payment of the fees. The entire degree program is taught by the faculty members of IIT Guwahati. These are the same faculty members who teach a very similar program to our BTech students. We also have a BTech in Data Science and Artificial Intelligence. So all this, along with some the NEP 2020 flexibility that is discussed in that, so early exit, all those options are available here. Then we also offer online MTech degree programs. So one such program is in Department of Civil Engineering, which is unique. It is not there anywhere in the country. It's on water resources and flood management. Right? So this is the only program that technically teaches these engineers of the public works department how to manage, how to mitigate these effects of these floods. Then another MTech program is coming, which is robotics and artificial intelligence. Right? So slowly we are moving towards giving more and more students opportunities to learn from IITs. We have limited resources in terms of classrooms, in terms of hostel accommodation, all that. But if we are doing this as online, there is no limit on that, there is no upper cap on that. Right? So in addition to IIT Guwahati, several other IITs are now doing that, offering online degree programs, online courses and all that. I'm sure you will enjoy your stay in IIT Guwahati and you will enjoy the lectures over the next 5 days. Please feel free to visit any department, any center or school that you wish. Maybe CET can arrange, I hope CET might be able to arrange some visit to very interesting laboratories that we have here, some state-of-the-art laboratories. Please visit, and I'm sure your stay will be fruitful. My best wishes to you and to the organizers. Thank you.
Thank you, sir, for your inspiring words. I now request you to felicitate our foreign expert, Professor GIAN Pidanic. Thank you, sir. We are honored to have with us expert Professor GIAN Pidanic, Senior Member of IEEE and Associate Professor of Electrical Engineering and Informatics, University of Pardubice, Czech Republic. His research spans signal processing in radar systems, bistatic radars, clutter modeling, and the optimization of signal processing algorithms across various applications. I request Professor GIAN Pidanic to kindly come on stage and address the audience.
Okay, good morning everyone. Thank you very much for invitation, and I would like thank you all of you that you allow me to come for next 5 days and provide you, I hope, some interesting information. I want to introduce my course, but Dr. Ashwini do it instead of me, so I don't want to make a repetition, but I just want encourage you about this course that I like interactivity, so please don't worry, ask me to anything, because I don't like words lecture, because it is mean that one people speaking, the listening. No, please interactive. If you don't understand something, just ask me, and it will be more discussion than lecture, because I think that is much useful than if you just listen and just follow my words. So please don't hesitate, ask anything, even during breaks and so on and so on. And I hope that will be very interesting for you, and I will show you that these two different words, what is radars, green energy and wind turbines, is more interconnected than you expected. Okay, thank you very much.
Thank you so much, sir. With this, we conclude the inaugural ceremony. Thank you all for your presence and participation. We will now have a tea break. Enjoy your tea we will resume the session at 11.
slowly, if everybody is there. So one more time, welcome you, all of you, and I hope that you hear me well, that my voice is strong. We'll see if it will be strong after 5 days. And in this lecture 0, I want to show you motivation, why we care about this problematics, and told you some details about courses. So why this course? This course we create due to long time cooperation with IIT Guwahati, because I closely cooperate with Dr. Gaurav Trivedi and partially with Dr. Ashwini. I am from University of Pardubice. I will show you where it's located, and I am head of department of electronics and radio system in this university, in faculty of electrical engineering in informatics. University of Pardubice is relatively small university, but everything in Czech Republic is small with comparison to any Indian city, so it is it is normal. We are a small city located about 100 kilometers east from Prague, so it is about 50 minutes by train from capital city. And why in Pardubice is so important for radars, even for last 100 years? It is reason is that in 1919 there was founded a company named Telegrafia, and from this period of times it is starts history of radio, electronics, electrotechnics, and all these techniques things. Pardubice. Pardubice is relatively small city, 100,000 people, but their work, I think, from 100,000 people, about 3, 4, 5, maybe up to 10,000 people works in industry with radio electronics. So during communism, the Pardubice was center of radars parts of Eastern Europe. So we developing radar, or not me of course, but there was developed radars for Eastern country like Ukraine, Russian, and all these countries, and it was developed in Pardubice. So there is really long history. I will show you later. So there is some link to our university, faculty, and departments. How professors say, it is about networking. So if you want to cooperate in anything, just let me know. Just you will see at the end of the lecture always my email, so you can send me email anytime, and we can make any arrangement. If you want any data, any information, just please let me know, because networking is on this way very important. Okay. Where is located of Pardubice? I just make one short video. We are in center of almost Czech Republic, so you can see location of Prague. There is location of Pardubice, and it is about 100,000 people, and we are located. Our faculty is like directly in center of the city. So we are small faculty. Our history is only about 15 years old, but we have strong cooperation with industry, and a lot of professors are directly come from industry. So it is really good for us. It is really good to opportunity with working with industry. So our main partners are from industry, and it is related just to radar technology, how we will see later. So why this course? Why is this so important? Because you probably know what's radar doing: detecting targets, controlling airspace, or there is lot of different application. But it is one side of question. Second side is renewable green energy sources rapidly growing. How Professor mentioned, every 1 year in India is growing industry about 4 gigawatts per year. So it is mean that not grow only number of wind turbines, but also their sizes. And it is start be problem, because imagine wind turbine is big object, and blades, it is rotating object, and this rotating object has similar or same signature for a radar like flying target. So generally speaking, if you have some, like example, enemy plane that will be close to some wind turbine farm, you will completely lose detection. You don't know where is this plane, because you will see just wind turbines due to stronger reflections from wind turbines instead of reflection of this target. So it become very big problem, and especially where you can install wind turbines in area that are free, very strong wind, and where you install radar, where is free area because you won't see longer distance. So this mutual coexistence start be really crucial thing, because you need to follow how we can deal with this coexistence. Because of course we need green energy, but we need safety in airspace also. And both together it is not easy to do it. So it is just motivation why we doing this course. On this course I work with my colleague that I want to mention, Dr. Jurica, that made PhD thesis on this problematics. So a lot of picture that you will see with signature JK, it is from his thesis, and it is his contribution or mutual contribution. So in one sentence, there is a huge impact on radar performance, not only in air traffic control, but also of course in military air traffic control or air defense. So we need to mitigate this influence. And next 5 days we will talk about how we can, first, before mitigation, of course, we need to analyze what is impact. How looks this impact? Because you can imagine that wind turbine is rotating, and this rotation gives you in any time with any position with respect to radars always another reflection. So it looks almost like random movement from point of the reflection. Of course, speed of rotation also change rotation, and so on and so on. So there is so multiple variables that is not easy to predict what will be behavior for mitigation techniques. So I will show you slowly how we continue. By the way, I have one question. Do you have some experience with radar signal processing? Do you know how works radars? On which principle? I just ask. If answer is no, never mind, because I will show you. I'm just asking if you have some experience. Okay, perfect. Thank you. So I am most worried about this part, because my second lecture is about radar system and signal processing, and it is very, very long and will be very, very intensive for you. So please don't hesitate, ask me anytime, because you need to understand how works radar, because if you don't understand, then influence of wind turbines to radars will be hardly to understand, if you get my point, because you need to understand how it works. But don't worry, we will handle it. I hope that have a lot of picture and it will be, everything looks nice. So we choose a methodology how we'll deal with this, because of course people found it that there is some problem with reflection of wind turbines close to radar. So first we realized that we need to make observation of real wind turbines in classic environment and check it how looks like this reflection, how describe this phenomena of this reflection. Then we just think, okay, so we take one measurement, so it is mean that you need design a measuring chain, you will go outside, you will measure reflection of wind turbines by some radars, you need very expensive equipment for this, and so on. And now imagine, you will come to some place and there is no wind, so wind turbines stop. Okay, so you will come next day, and it costs you time, money, and of course you don't need only one management. You need thousand and thousand measurement for design of mitigation techniques, but it is not possible. They even don't allow you go too close to wind turbines because very often it is protected area. So we just think, okay, so we will try design some wind turbine model or simulator. You call it model or simulator, and in the last 3 years we designed this simulator, and we designed this simulator that you will place in our simulator radar with specific parameters, wind turbine, one or more, and output is reflected signals from these wind turbines. So we can set a lot of parameters that you will see later, and this could be same results or very similar results like from measurement. But you don't need to go outside, you just run software, set and watch a result. So it is much effective and it not cost you almost anything. Our simulator was designed in MATLAB because I think that in academy is very usual environment and it is easy to use. So of course we must be sure that our simulator is good, that produced output is same like from real turbines measurement. So we also measure some real reflection and make comparison, verification of model with real measurement, and I think that you will see later result that is not perfect of course, but very good similarity. So we can use it for designing for mitigation technique. Okay, our system for mitigation of wind turbine influence on primary radar system is based on extraction features, prediction features, and filtration. It is just 3 base steps. You will see this later. And after this we make model validation, and now it's used for any scenario. I will show you later results about 4 different scenarios in different places of Czech Republic and one from Austria, where we make comparison of our simulator with real measurement. So green energy spreading around the world last 30 years, and I think that is important part of our life. I think that you can also see it in your country that this topic is very modern, and number of, I will focus only on wind turbine, not solar plants and so on, because it is my topic of lecture, and wind turbines spreading everywhere, especially in area where is strong wind and like solid wings, not any, just only for a few minutes, then nothing, and so on. So it is clear that it is good source of energy, and this massive expansion of wind turbines negatively impacts functionality of radar system. especially deterioration of their detection capabilities or target masking. On the right picture, you can see some wind farm, offshore wind farm, that could mask you almost any flying object, because imagine that there is no synchronization of this wind turbine, so any wind turbines rotating with another speed, another blade position, and so on and so on. And if you will see reflection on radar of these wind turbines, it will be like one big target. You don't see anything, just anything. And it is very dangerous, especially on coast. If you will have some enemy, something, always come from coast, so you need to see. But we will stay in civil, even for air traffic, of course, because density of flights is also increasing. The like limits between two aircraft is still minimizing, so they are close to each other, so you need to be really sure where is your location of your target. So this course, this will be just few brief slides. This course will take 5 days. Lecture part is about 14 hours, 1 hour 60 minutes. Tutorial part will be about 8 hours. Of course, some lecture could be shorter, some longer, because I try to adopt it, but it is first time, so be please patient with me a little. Today will be, after this lecture 0, how I call it, will be lecture 1, where I focus on renewable energy in India. I just prepared about 7-10 slides just for you, because you will see where is windy region, what is number of wind turbines, and so on and so on. So it is adopted for your country. Then I will briefly describe general radar system description, their application, purpose, and classification of radar system, because I will focus only to primary radar system, but there is a lot of different type of radar system. And few words I will say about the history of development of the radar. Second, or lecture 2, it will be during this afternoon. It is, I think, the most demanding probably for you, and it will be about signal processing in a radar system. And there is a lot of blocks with specific purpose that you need to understand. So please, anytime, just stop me, even during my talk. There is not any issue, just stop me and ask me if you have. And I hope that will know all answer, and if I know answer, I will quickly answer you. So we will finish first day on first part of tutorial 1, and it will be completely in MATLAB. So if you can bring after lunch your laptop, just bring laptop, and I will share link with MATLAB, and we will work together. It is much better. Second day will be about description of wind turbines, because okay, I'm talking about wind turbines, but wind turbines is divided to many parts, and each part have different influence to radar. So we will need this description. We will talk about principle of operation, usage onshore, offshore. We will talk about radar cross-section of tower blades from different direction, about spectrum. By the way, I suppose that a lot of you is from electrical engineering, so I suppose that almost all of you know Fourier series, Fourier transform, you know what is spectrum. It is perfect, it is enough, we don't need anything else. Okay, we need to know what is spectrogram, but it is same, just changing spectrum in time, so it is enough. But don't worry, we will not compute it anything, it is just I need these terms. And then I will discuss also mitigation approaches of wind turbine and state of the art, because a lot of companies is interesting about these topics. So I found about 8 up to 9 companies, and I will show them these products for mitigation of this influence. Then we continue with lecture 4, and it will be about design of simulator. So we will make description of geometry of wind turbines and radar system, or wind farms, simulation of received signals, deep analysis of wind turbines influence. But it will be all, like to say, in theory, about mathematical description of this model. There will be a lot of formulas, but don't worry, I will explain you by words, so it is not important to, how to say, remember all this formula, because I don't know how you, but I don't like any memorization of formulas, because it's necessary. You need to understand principle. Formula, you always can find it in some book, so it is not so important. Then we continue with tutorial 1. It will be again related to some radar equation, power budget in radar, radar resolution, matched, unmatched filtering, and so on. Day 3 will be about modeling, development of simulator, design, testing, validation, block scheme simulator, and mathematical description. Then we will continue with tutorial 2. That will be on usage of simulator. Again, all MATLAB, so please laptop with you tomorrow. Every day, generally every day. Day 4 will be lecture 6 and tutorial 3. It will be challenges with wind turbine measurement in the field. I will show you that it's not easy. Of course, you need to have some radar. Radar is expensive things for $1 million, and it is not so easy. Say, okay, just take radar and when we go to measurement. It is not possible. So we design a measurement chain based on software-defined radios. It is small boxes only, and I will show you how set up, how prepare all this measurement chain, and then what you need for this measurement chain. Of course, it is also, you need some equipment, but it definitely is not so expensive like the wall radar. And on tutorial 3, we will make simulation of real case scenarios. So I have prepared tutorials where I show you where is wind turbines, and through some GIS software like maps.com or Maps Google or something like this, how design, where I should put my measurement, how I can be close to wind turbines to proper results of measurement, and so on and so on. It is not easy task. Also, you need to be worried about permission, because you can't go to any place and just start transmitting some energy, because I think that it will be really big fine in any country in the world. So I will describe you a few words about this one. And day 5 will be held to mitigation of wind turbine influence by pure software solution. I will show you that exists many hardware solutions. Again, they are definitely more expensive, or you need to make modification on present radars, and it is also very expensive, long time goal. So we develop with colleagues mitigation technique that is purely software, and it is relatively easy to implement, because you don't need change any hardware in radar. It is just in software. So I will show you, and it will be lecture 7. And tutorial 4 will be, it will be presentation of complete mitigation algorithm of our. Again, developing in MATLAB. I will share all scripts, all applications, so you can, even after finishing course, you can play with this without any problem. And we will end with lecture 8, but it will be just conclusion, discussion, if you like it, if you don't like it, where I should improve, and so on and so on. So it will be more about your opinion. So totally we will spend together for 14 hours with lecture, 8 hours with tutorials. So I hope that you will enjoy it. And the end of each lecture, you can see my contact information, so you can contact me anytime on email, just anytime, it is no problem. Okay, so it was lecture 0, and I will continue with lecture 1 or now, yes, lecture 1 now, yeah. Because honestly I don't remember what it yeah, but we have now lecture 1, so it is good. So what we need, okay, what is wind turbines for us? Wind turbines are not only obstacles, but the dynamic scatters that can create detection losses, masking and fault tracks. So we need first to understand of this impact phenomena, and this impact phenomena is divided to many parts, how you can saw it later. So first we need to make analysis of the radar signal or data, because later you will see that we are not working only with signals that we receiving by radar antenna, but very soon after some pre-processing we just convert it to data, because of course 0101 it is better for processing for us this data, for storage, for anything than analog signal. So it will be first step. Then for us is important modeling this phenomena, because how I already explained you can't go anytime to specific position, you don't know if will be wind turbine rotating or not, and so on. So we need to model this phenomena, but not only for one scenario, but for any combination of any input parameters. And it is our plan to future. You can, if we will collect a lot of data, make a lot of simulation, we can gather all these outputs and try use some machine learning techniques for some mitigation based on like automatic adoption of this mitigation. So it is really important how to say easily, without measurement, without data, you can't do anything. So it is main importance why we designed this simulator. So design of second after analysis, of course, is designing of mitigation techniques, and these mitigation techniques could be based on special hardware, on signal processing method design, but always all possibilities that you choose must be adaptive, because imagine you will make some mitigation algorithm that works perfectly for your settings. Now wind will be quicker, it will be quicker rotation, and your mitigation just fail because it is not adopted. And this adoption is really big problem, because there is so many influences that it looks almost like a random behavior. But I think that we was successful, that we split to some important part. So solving all these problems restore the radar wind turbines free performance, and we again can see even in geographical areas where is presence of wind turbines. So first, something about global wind energy contents. There I want to show you that due to high spreading of installed wind power capacity, so it is mean a number of wind turbines, influence on radar will be increasing. So I think that is relatively important topic, because even now we make study before 3 years when one company have installed small wind turbines close to weather radar, and we have in Czech Republic, we are small, only 2 weather radars because it is covered the whole Czech Republic, and it was about, if I remember well, 5 kilometers far away. And it was old wind turbine, small one, I don't know, 25 meters, 30 meters, nothing big one. And they want to install some about 90 meters tower with blades about 40 meters, if I remember well. And now people from radar station, weather radar station, discover, oh, you can't get permission to making one because it will influence of this weather radar. And it was true, influence. Not so big influence in this case due to mutual position, but still there was influence. So, and this like problematic places will be increasing, of course, because if number of wind turbines increase, there will be also increasing number of like conflicts between this. And there I want to just say that what is biggest player in global market. You can see that China is biggest player because they have in some area where it's really windy, so it is easy for them. Second is USA, third is Germany, and fourth is India. So I just want to present you that you are in top 5 of installed wind turbine energy. Later I will show you where, because I already made these discoveries, because I think that in Assam there is almost not any wind turbine installed, not many of them, because there is not area with stable wind direction, something like this. But I think that almost is in south, how we will see later. So I think that in India, for India will be big problem in close future also. On this slide I want to show you trend of onshore and offshore turbine size. You can see that development of offshore starts in 1990, something like this. Before this it was some maybe experimental, but definitely not commercial. Size of wind turbines was 35 meters. With blade, if tip of blades, it is about 50 meters, and power about half megawatt, relatively small one. Then 95, 2000, 2005, we have already 3 megawatts, about size 125 meters, then slowly growing up to 2020. It is about almost 200 meters and almost 10 megawatts, and in 2023 it is almost 300 meters and 18 megawatts. And now check this red red area. Uncontrolled space limit is 300 meters or 1000 feet. So it is mean where is uncontrolled space. So you can do it, not almost anything, but a lot of things. But everything under 300 meters or 1000 feet, it is controlled space by air traffic control. So the highest wind turbines is on the edge of controlling space. And if it will be growing, still growing, then we have really big problem. So it is not only academic question I want to just discover, and it is about offshore. And look on onshore, it is below. Onshore, it is oh, sorry, I just misunderstand. Onshore is of course a little slower, but offshore is bigger, because there is not so big problem on the sea, coast to sea. Okay, about some renewable energy in the Republic of India. This will be only about wind turbines. I don't discover any other green energy sources, because I suppose that I saw also a lot of solar energies and so on and so, but probably you know about this much more than me. So, India wind sector really rapidly growth at last 20-30 years. From history of development is early begins in 1980s, 90s, so you can see it is same like in the rest of world. Of course, you are follow your modern society, so it is global. It is global. So first modern wind turbines were installed in Gujarat, Czech region. Sorry for my pronunciation, because I don't know what is good pronunciation. In late 80s, and it was first commercial energy project. In 87, India was founded Indian Renewable Energy Development Agency, I call it IREDA, which financing a promotion of wind projects. From 2000, it is institutional support. It was formulation of National Wind Solar Mission in 2003. Stimulated domestic manufacturing and installation of wind turbines. So this means that you don't want, of course, buy all technology abroad because it is expensive, but you are start developing own wind turbines, own technology, everything by own. So it is always better for country than buy only things. There was also in each state, it was like state agencies and policy frameworks facilitated the development of wind farms. Three big regions where is a lot of wind turbines, how you will see later, is Tamil Nadu, Maharashtra and Gujarat. From 2009, in 2009 it is very interesting, you have installed only 2 gigawatts in the whole country, and in 2019, only 10 years, 31 gigawatts. So it was also like driven by Ministry of New and Renewable Energy, by favorable policies, international investment, technological advancement, and focus on reducing reliance of fossil fuels. So this, like how to say, government support means that this industry still will growing up. And India is big country, so it is mean a lot of airports and a lot of wind turbines in the same. It is not good connection, how we will see. In recent developments after 2020, it was set a national plan, and target is in 2030 that your country should have installed 60 gigawatts in 2030. I think personally it is set by National Renewable Energy Action Plan, and honestly I think that it will be quicker, because your energy industry growing every year about 4 gigawatts, and I think that you will fulfill this plan about 2027. So there is really big primary focus on this. There I found windy regions map, so you can see that on this area, I think that is Rajasthan, if I remember well, and in this area it is the biggest wind that is suitable for installation of wind turbines. So I don't know, do you have, please can I ask, do you have experience, do you see a lot of wind turbines in this south? Because I never visit south, I always travel in the north. So can you confirm me? Yes? Yep. Mm-hmm. Yeah, I think it. And also there is some mountains, I think, so mountains with combination close to sea, there will be windy region. Yes, 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 I think it, because of course I check map, but never not see in my own eye. So, and for this reason I think that in Assam around this there is not so windy, and it is also close to this highest mountain, of course, Himalaya, and I think that is unpredictable wind. So there maybe is reason, I don't know, of course. So I think that the majority will be installed in this area and maybe in Rajasthan in this area. No, I don't know, it is not me. Maybe. No. Yeah, yeah. But it is my PC. But it is go from this PC. It is not my PC. Never mind. I think that they will shut down soon. So there I found it some. By the way, I don't told you. Each source in my lectures is with citation. So if you want to check sources of all these links, you can easily do it later. I also will share this PowerPoints. I will prepare PDF so you can check it later if you are interested. So this is pictures from Gujarat, Tamil Nadu and Karnataka. There, okay, and now I've switched down internet, so I will connect it. Give me seconds. Okay, check. Just for quick explanation, I don't use it maps.google.com, but this mappy.com, it is Czech version, and there is one good functionality. You can saw it line of sight between two places. You can measure distance and it will show you digital elevation model. But Google don't have this functionality, so we use this one. It is very handy. Of course, I have it now in Czech, but you can easily switch to English, so don't worry, but it is good tool. Of course, if you like Google Maps, you can, but there is not this functionality. And Czech, I am now in south. And if I will make just zoom, look, all this is wind turbines. Check how many wind turbines is in this region. I was very impressed about this because it is everywhere. And imagine, oh, you don't saw it. Sorry, you should tell me. Okay, I need quit presentation and show him up. Sorry. Okay. So one more again. I am this region. It is Tamil Nadu. Yes. Thank you. And if I will zoom it, Czech. I was really impressive. It is wind turbines is just everywhere. And check about resolution. This is 800 meters. So okay, it is about 1.2 miles. So it is almost everywhere. Density of this wind turbine. Probably it will be some small. Honestly, I can't find any information which type, which developer, but it is just everywhere. I don't know. Do you visit this place? Somebody from you? So it is just everywhere. It is almost thousand of them. So it is exactly fit with map of wind region. Okay, now few words about radar. What is radar? I know that exists maybe 1000 definition what is radar, so I just take one from Britannica because it is very well known encyclopedia, and I don't want to use my words because encyclopedia is encyclopedia. So radar is shortcut of radio detection and ranging. Detect and tell me where is it. Of course, it is just very brief because in present times you don't know only information about where is target, but what is speed of target, what is which type of target, classification, and so on and so on and so on. So of course this is just from all the definition. By the way, when do you think it was developed first type of radars? What do you think? Just some guessing. Exactly. During Second World War. Exactly. I have one picture exactly, because I think it started. I don't know honestly if Germany or England, but it was some mutual combination, of course, because one attacked, second they defense. So it was during Second War, exactly. So this radar is device used for detection, tracking objects at long distances by transmitting high frequency radio signals and receiving the reflected signals. So it is definition from Encyclopedia Britannica. Radar system it's so many kind of different radar systems for short distance, long distance, automotive industry, military, and so on and so on. So tell you where we can use it. Answer is almost everywhere. It is just you need to adopt your radar system for purpose that you need. Exactly. Even if you go, I will make little fun now, if you will go to bathroom, then is some sensor for turn on water. It is also some kind of radar system. But it is just joke. Okay. Radar system, there is some base block scheme. Please, this is very introduction block scheme of radars. Imagine that in each block it is 100 of small blocks interconnected together. But definitely it is generally starts with transmitter, because you need something what transmits electromagnetic wave to space and get reflection. So it is transmitter. Transmitter include designing of this wave, because it exists, maybe I know about 30, 40 different kind of waves for transmission. And again, why so many? Each has different properties for different type of targets, and so on and so on. So transmitter then go to antenna. This is device, call it duplexer. It is switching between transmitting and receiving, because when you transmitting power, it is really big one, because you need the long distance. And if you are receiving, it is, I will not call it small, it is almost zero, because imagine that a power decreasing with r, where r is distance, r squared. So r squared one way, r squared second way. So it is really small value. And for this reason, after you stop transmitting and waiting for reflection, you need to switch this duplexer. So this is disconnected, because it will destroy your receiver. During transmitting, if this power goes to receiver, it will be completely destroyed. You will just see fire probably. So after transmitting, you will receiving part, then there you made AD conversion. So there is analog, there is still some mixer, there is some analog devices, analog part, but after this we work only with IQ, so with complex envelope of some baseband signal. There is signal processor, and there is a lot of things you will see later on lecture 2. Data processor, and there is also local oscillator that makes synchronization between transmission and receiving time, and synchronizator, and display. And display is for visualization of results. And there could be 4 different types of visualization. And after visualization, this from process data, it could include tracking algorithms and so on. This could be communication outside, because you can have it network of radars, and this go to fusion center, and this fusion from different radar is fusion of data. Okay, thank you very much. Then there is some another things. It is like power supplies. This is like controlling mechanism when if radar works properly, if is there not any issue, and of course antenna gear, because we could have it radar with static antenna, just watching to one side, or rotating antenna. So it is depends. So it is a base block of radar system, and details you will see in lecture 2. So what is main purpose of radar system? First, navigation and safety for us probably is most important. So it is assisting aircraft, ships, vehicles navigate safely, detection obstacles, other vehicles, and geographic future. By the way, before 2 weeks I just talked with one friend that working in automotive industry. I am just asking, how many sensor radar, like different type of radar or radio sensors is in modern car? So what do you think? How many of them? He told me about 70, so you are really close. 70, 100, it is depends. So yes, a lot of different sensors. If we talk about radars, I think that each car, if you has about, and unit view 360 degree, it is about 6 or 7 of radars around the cars. So it was really close. Then it is navigation and safety. I think everybody knows, because it is part of our life, so we know it. Then it's military and defense. It is for detection and tracking aircraft, missiles, ships, potential threats. It is same principle, of course, but these military radars will have much better improvement, resolution, EMC protection, and of course some protection about listening, some coding, and so on and so on. But in principle, it is similar type of radars. Then we have weather monitoring radars. These radars works totally in different frequencies. Why? Because we need to see through clouds also. So it is lower frequencies, how you will see later, and it is for detection of storms, clouds, and any atmospheric influence, of course. Then we have air traffic control. It is managing and monitoring civilian and military airspace. And why I split air traffic control and navigation and safety? Because navigation and safety is usually primary radars. So primary radars don't require cooperation between radar and target. It is just send wave, get reflection, and get information from reflection. But air traffic control, usually, maybe you know ADSB, it is device that is placed in aircraft, and radar on ground send information. Where are you? And this device answer, I am here, and send information. So do you see this difference? There is two cooperation sides. So for this reason I divided two groups. And then we have remote sensing, and it is Earth observation, geographical surveys, environmental monitoring, and so on. Google Maps, Google Earth. It is radar also. We call it SAR radar, SAR, synthetic aperture radars, and it is for monitoring ground, but it is also radar. Okay, when we can see radar application in real life? Okay, navigation, I already mentioned it. It is surveillance radar, precision approach radar. This is another special type of radar where it's used only on airports. If airplane is ready to land it, there is one special radar that told me with high resolution where is it, and if you are in good line for landing. So it is just about landing and starting, not just about landing. Then we have marine, coastal, shipboard. Of course we have radars also for underwater work, sonar, and so on and so. So you can see the application of radar is many of them. On military we have like battlefield radar, surveillance, weapon mounted radars. Then we now is become popular radars for detection of small, slow flying object, UAV, drones, and it is a really big problem. But you can probably imagine why. How you want to see drone at the distance 5, 10, up to 20 kilometers. Drone, it is this size. And imagine that you have like your radar, there is some wood, some big tree, and I am enemy and flying with drone. And there is wind, and tree do it this one. How you can recognize from drone this movement? It is really hard. And this very short range radar, it is now become very popular, but you can also saw it if you see conflict between Ukraine and Russian, because it is just full of drones. It is like a war of drones looks like almost. So then we have automotive radars. So, and there I have list of few examples: adaptive cruise control, forward collision warning system, blind spot detection, parking assistance system, automatic emergency braking, pedestrian and cyclist detection. All this one term, one specific sensor, one specific radar. Then we have police radar for the speed measurement. Okay, we don't like this kind of radars, but it is also important. And then I don't know if you heard about true wall radar. Don't heard? It is this one. It is from company Retia. It is also from Pardubice. Honestly, I don't know any other product, and it is used for police or anti-terroristic unit, because you just take it like this, place to wall, and you will see if somebody is on other side. But there is big but: if you have wall with full of iron bar, of course will not work. So it is working only somewhere, because of course it is like shielding. So but I saw it in action, and if you have, like, typically in US every building is relatively thin, if you understand me, from wood, so it is perfect. They use it, I know it, because the company confirmed it. They use it for detection of immigrants or something like this behind the wall, and so like this. So it is very interesting radar, and it is based on UAB signal. It is ultra wideband signals, because you need really huge bandwidth for detection of person through wall. Okay, there is a base classification of radar systems. We could divide it active radars and passive radars. Active radars transmitting energy and receiving echoes, and it is active because he needs to send energy and of course receive echoes. It is typically its primary radar system. It is this air traffic control, weather radar, and so on, how I already show you. Then we have secondary radar system for air traffic control, and it is this type radar that require small devices, so-called responder on airplane. So radar sent information: where are you? And he answered me, I am here. Where are you? I am here, and so on. And this communication is in every few seconds, in a very short period of time. So air traffic management, air traffic control always know where is target. And when I just imagine some big airport like Delhi, Mumbai, and so on, where is, I don't know how many targets around, but a lot of them, you need really good view where you have individual location of planes. Then is special kind of radars, and we call it passive radars. Do you know passive radars? Passive radars is radars that use transmitter of opportunity. It could be, it is usually bistatic. And what is mean bistatic? You know that monostatic radar has transmitting and receiving part in the same place. It is same picture that I show you sooner, this block scheme. So I have just one antenna. This antenna is used for transmitting and receiving. It is one antenna. But bistatic radars use separate antenna. And this separation could be few hundred meters, 1 kilometers, or 20, 40 kilometers. And how it works? Generally, your radar is just receiver but not transmitter. And you can say, okay, if I didn't transmit anything, how I can detect targets? From which? From so-called transmitters of opportunity, and this could be like example TV transmitters, radio transmitters, because they are everywhere, because or GSM transmitters, but it is not so often because GSM transmitter, they don't have really long distance because it is a lot of them, but usually distance is few kilometers maximum. So usually it is DVB-T, on previous time it is analog TV or FM transmitters from radio, because there is huge coverage, generally almost whole country, and you just place receiver and listening, because if some fly, how to do it, if it's this receiver and there is some transmitters of opportunity like television receivers for the DVB-T signals, and your targets fly around these transmitters, these signals from transmitters is reflected from target, signal is reflected to target and go to your receiver. And also direct signal, and from combination of direct signals and reflected signal, you can compute where is target. What is big advantages of these radars? What do you think?
Radar seeking missiles, because there are missiles that seek where from the signal is emitted and they can destroy it.
Exactly, exactly. You are not transmitting. Nobody knows where are you. So I think that there is clear what is main purpose, military. And passive system is not so very often used, and I must say that I am little brave that in Pardubice we have one company that developing these passive systems, and is called it ERA. I will show you later. Then we have multi-static radars. It is the highest level of type of radars. Imagine you have multiple radars in a network, and they fused information together, and you have the coverage of the whole big area. And it is this one. Okay, now this few slides about history of radio technology in Pardubice. How I already say before, more than 100 years was founded Telegrafia company that developing classic radio systems, old stuff. There I found some old analog radio system. It was AM, you can see. By the way, we have one museum in Pardubice. One guy is really fan of these old things, and all this radio is functional. It is more than 100 years and it really works. You really can. So it is amazing. Of course, this not looks like that working. It is probably not this one, but he make reparation and works. This this company was in 1945 renamed to Tesla Pardubice, because after end of the war, it's in Czech Republic it was start of communism regime due to influence of Russia, and lot of company that was private is now state, so it was renamed just for why it was renamed. In 1950, what is very important date for Pardubice, was founded Radiolocation Research Center Opočínek. It is about 2 kilometers or 5 kilometers far away from Pardubice, and there was only one main purpose of this research center, developing of radars. Really focus only on radars. And it was of course part of this big Tesla company, but it was relatively independent part. It was just research center. So imagine in our small city, 100,000 people from 1950s, there is just focus to radars. and chemistry. Okay, if there will be my chemistry colleagues, they will don't agree with me, but from 50s also in chemistry. So chemistry and radio. There is some example of their products. So first products, it was radars PR1, and it is Czech name Kopáč. In 1970s was developed Ramona. In NATO, I think they call it softball. I think that you know why I call it softball. And this range in 1970, it was about 450 kilometers of these radars, and it was completely passive. It was passive, just passive. And later, next generation after Ramona was Tamara. It is in 1980s, and they call it trash bin. I think that you can also recognize why. And one funny thing, Ramona and Tamara, it is women's name. And I heard stories that, of course, in this company, 90% of people was men, because it is techniques. And only some few females working on this, like some in technician position or secretary and so on, and it is name of these women. I don't know if it's true, but here that is true. It is just funny things. And later, it is in 90s, so it is after we get independence in 1989, and it is new version of Vera. So again, Ramona, Tamara, Vera, again women name, and it is third generation of passive radar system. I will show you last version of Vera and G later. So in Pardubice is many of radars company. I just want to show you example of the biggest one with biggest influence. It is Retia, Eldis and ERA. ERA focusing, and all this company, almost all this company is like divided from Tesla company, if you understand me. The big Tesla company was like separate to some small companies, and it is this one. So Retia company is specialization is in advanced air defense system, including command and control system, radar integration, and short-range air defense solution. It is focusing more on military solution, if I can say, but not only on developing radar, but a lot of other things also. But of course, I just present you what is important for us. Then second is Eldis Pardubice. It is significant player in air traffic control and radar technology. By the way, I will show you later that Eldis now control through their radar system more than 95% of Indian airspace. So if you are traveling in India airspace, it is controlled by radar from our small city Pardubice, from Eldis company. Last is ERA. Its specialization is in passive surveillance and multilateration systems. It is again a lot of military, but also they develop SQUID system, and it is identification for system on airports, because you know on airport there is not only planes, but there is a lot of cars for pickupping, I don't know, baggage and so on and so on. And each this car have like small antenna, so you know where you can go, where it's not dangerous and so on and so they don't develop only military, but also for airports. Okay, some few details about Retia. They developing, presently they offering 3 type of radars or 4 types, maybe more, but of course sometimes can be not publicly available. And I know that they develop now new generation also. So there is example of their products. It is Regard. It is 3D radar. It is family of radars based on AESA. AESA is antenna active phase array. So it is mean it is not classic antenna. It is active phase array antenna, and this is the wall radar. I think its weight is about 60-70 kilos, so 2 men can easily just drop it and use it. It is detection, it is short range radars about 30 kilometers, if I am not wrong, 30-40 kilometers, and it is suitable for detection also for drones. I think that they developed before 5 years, something like this. It is relatively new product. Older product is Revisor. It is 2D short range radar for air defense. Again, this is radar that is rotating, and this could be static or also rotating. It is depends on how you want to use. And there is my already mentioned this Retvis detection person behind a solid obstacle, so you can see this one. This is about first generation has about 12 kilograms, and this next generation it is about 2 or 3 kilograms only. It is relatively light, and it is of course works only on battery for about 5 or 6 hours. But don't expect that you will see on your screen like the whole person, because detection is principle of detection is on detection of your heart. So you will see only red dot or something like this. We are not in movies. Second company is ERA. It is specialization, research, development, manufacturing of radar system for military and civilian application. And there is newest generation of Vera NG trash bin. If you remember from last slides, it is not looks like trash bin this one, but it is last generation, and it is completely passive system. Also, I already mentioned Squid, ATS safety system. You can see it is placed on the roof of car. And then there is PLES system. PLES system is like how to say, long range radar system that like warn you like 500 kilometers I found can detect targets. So it is really big antenna, massive antenna, and it is developed with some military institute in Czech Republic. Sorry?
Using like S400 radar.
Yeah. So it is this one, but this and this, it is just pure military. And the last one is Eldest company, and there I just want to show you where it's placed. I think this company use on radar system for air traffic control only and surveillance. So they didn't, I think, develop so many military systems. It is primary surveillance radar. It is this one, but please, I show you this one that is military radar. This is just antenna. Of course, radar is in this box, if I can say. But we call it, of course, that is radar, but it's just antenna of radar. So it is this primary radar system. This is this secondary radar system, so that requires this device on the board. and this is this precision landing system, precision approach system, how I told you. So you can see all three together, and you have covered the whole airport with everything. So, and I found and discussed with them, because our faculty cooperate very intensively with LDs. We have mutual research project. Also, we cooperate with ERA and RETIE. So we very often visiting, or our students visiting, these all three companies. Until now, it's 14 radar system installed at 2 major airports in India. So covering, okay, not 95%, sorry, 90% of airspace. But there is some future plan that about 2026 up to 2030, another 20 additional airport radars, and then will coverage by radars from Pardubice 99% of your airspace. So a lot of people from LDs, of course, travel to India, because you need to install, you need to maintenance, and so on and so on. And when I coming to Guwahati, and after just we landed, I just watching from window, and wow, it is in Guwahati. I am pretty sure, because of course my camera is not so good, so I can't zoom it very well. But if you can saw it, secondary, primary, I think that is in Guwahati is also radar from LDs. I am not 100% sure, but 90% I am sure. After I come back to Czech Republic, I will ask in LDs company if it's their installation. There is zoom, but I am sorry, of course, it is just from camera through window. So, what is out now? So it is end of first presentation, and I am not sure if we have time. I need to check. Almost, if you agree, we can stop there, and now will be 1 hour break for lunch. So please enjoy lunch, and after 1 hour we will continue with second lecture. Okay, thank you for your attention. And if, of course, if you have now any question, just let me know. Discussion, remember, discussion. Okay, thank you. So enjoy lunch.
We will resume the session
Is it
at
okay?
1:30.
Yeah, this one. Okay. I can leave it there. And my stuff also. It's very hard to remember.
So the meaning of Sarita is river.
Okay.
River.
Okay. It is better. But I don't want to call you river.
You can.
No.
basically it does the beam shaping and all.
Okay, okay. Send me some information because we are now interested in these things also. Will be nice. If you just send me some information if you can.
Yeah, sure. Yeah, take a rest.
Okay, like this presentation because I don't like just how we define transmission of pulse and so on. So I think that this is maybe tough lecture from the whole series due to missing experience from radar, because usually, like in my study program, we have 3 semester and 3 different courses, and I need squeeze this 3 semester course to 1 lecture. So it will be tough, but I have a lot of picture, and during tutorial I must say I will share all this MATLAB codes, and it will be just visualization. Just forget about formulas, try just to understand principle, and if you have any question, of course we could discuss during break. It will be best one, because now I have about 80 of slides, so it will be a little tough out, but I think that we can handle it. So always I will start with our central question: how do wind turbines interact with primary radar systems? To answer this question, we need solid understanding of classic radar. So we need to know how is measured estimated range, how target received, how radar receive echoes, how is measured angle, radial velocity, what is limits, what is performance, which power I need to transfer to detect some targets, because of course it is clear that if I need to detect some big plane, I don't need so big power because it is big target. If you want detect UAVs, you need some different type, and of course it is also related on distance, and there is about, I will make joking, 100 parameters of dependency of all these things. So I want on this lecture show you some really base thing that you will use it later on other lectures. So in case that you will not understand something, don't worry, then will be practical examples and more will be clear. So what is aims and learning outcomes? It is this. Now we start with description of basic architecture of primary radar systems. I will explain you how primary radar measures range, azimuth, elevation, and radial velocity. Also, I need to highlight what is resolution and ambiguity of measurement, because we could have, how you will see, ambiguity range and unambiguity range. So it is 2 different things. So it is also very important topic. Also, I will show you some videos of interpretation of basic radar displays. We call it ABC scope or PPI. We will see later. Then we need to understand how quantitatively we explain radar equation and RCS. RCS is radar cross section, and this describe you generally size of target in square meters. Then I will let you just brief information about about signal processing chain. So what is pulse compression? Because pulse compression is related to resolution of radar. If your resolution is 1 kilometers or resolution 30 meters, it is big difference. Of course, it is depends on then size targets. What is Doppler processing? Maybe you know what is Doppler frequency. Doppler frequency, from Doppler frequency, it is shifting in frequency, and from Doppler frequency we can recognize how fast, what is velocity of target. What is CFAR? It is constant false alarm rate. What is tracking? And so on and so on. So we will start. So basically transmission and now we are on start. So imagine that we have radar and now it's transmitted our energy to target, to space, if there is some target or not. And this transmission of the signal could be continuous wave or pulse. And now if will be continuous wave, we call it usually CV radars or FMCV radars. And I just want to inform you, we will not work with CV radars. Now I will focus from these slides only to pulse radar system. It is basically all primary radar system, majority of them working on pulse regime, something like this. So now I will, when I call about radars, it will be always in pulse system. So there is just some brief example. Imagine that is this our radar, and radar, this is coverage area. It could be 1 square meter, it could be big one, it could be 2D radar or 3D radar. It is depends if my results from detection is only range and azimuth, or azimuth, range and elevation. So our signals that is transferred from radar and spreading to area, of course not how to say, not only reflect energy from our target of interest, but from anything, from environment, from ponds, from woods, from mountains, even from clouds, how you see, from storm, I don't know, everything what is inside of area of interest, it will be reflected back. So you can imagine that what is included in the received signals? Reflection from everything. And now, in real time, you need to decide, okay, it is target, not target, it is reflection of environment. We call it reflection from environment, clutter. So it is what I don't want in my signal, because of course it could mask my targets. Because imagine that you have some small UAV, and this UAV flying like this, and this will be some metal solid wall. Forget about detection, because this metal solid wall will have so strong that reflection that will hidden your small target. So first step, of course, in radar signal processing is detection. Then is from detection we will make measurement and processing of parameter. And what is base measurement and processing parameter? It is range, measurement based on transmitted signal. And how do you think that we measure range? When I transmit some pulse in specific time, then it's reflected and travel back. We measure range based on delay of signal. How we can compute the delay? From cross correlation of transmitted signal and received signal. I get a delay, and if I have delay, then I know that speed is speed of light, and I can easily compute range. But it is so-called slant range, because you know range, but you don't know from which direction. Don't think that radar works in XYZ coordinates. It is only on polar coordinates. Of course, we could transform to XYZ, but you need more information how to do it. So it is range. Then is angle position based on directivity of antennas. If you will have 2D radar only, then measure only azimuth. So, okay, I know range and I know azimuth. So it is vector. Okay, there is clear information and relation where is target. If will be in 3D, then we have also elevation information. So generally you can have 2D or 3D radar. Okay, so we know position now of our target, but it is not enough. I know if target, what is speed of target or velocity. How I can do it? You know that my transmitted signal is in some carrier frequency. I don't know, 3 gigahertz, 5 gigahertz, 10 gigahertz. It is depends on frequency band when my radar operated. And if I will send, how to say, signal to my target, it will be target, that is movement, reflected signal will have slightly shifted frequency. Why? Due to Doppler shift, because it is moving. So it is clear if target is not moving, Doppler shift is 0, because it's not moving. If will be moving, there is some Doppler shift. And from Doppler shift, I can compute speed of target. So basically say. And I will take care only about monostatic system setup radar. So it is mean that I use only one antenna for transmitting and receiving. Not bistatic, because in bistatic configuration is it in even more complicated, and it is not necessary for our case, because in ATC I don't think that exists any bistatic solution. I don't know this solution. So in ATC we use it only this monostatic solution. So I will continue. There is example I will show. I already show you in first lecture. Example of typical primary radar system. I put again because there is also system parameters. So this radar system from company Elbis RL2000 that I have suspicion is also in Guwahati, work in S-band. So it is bandwidth from 2007 gigahertz to 2009 gigahertz. So it is the working frequencies of this radar. It uses diversity transmission, short and long pulses, with power 14 kilowatts. So you think, oh, it is really big power. Why? Because this pulse is really short. It will be some microseconds, it will be some 200 nanoseconds or something like this. So it is big power peak, yes. So also this radar has azimuth coverage 360 degree. How is possible? Rotation of antenna. Elevation coverage up to 40 degrees, so it is mean also make this movement, but only to 40 degrees. Why? Because usually you want to detect all target that incoming to your side, but not from up. So it is like typical parameter. And range depending on configuration. It could be like their range. What is detectability of target is like 80 kilometers, and range of course depends on size of target. You can't say, okay, my radar could detect target at 80 kilometers. It is not true, because imagine Airbus for 500 people, okay, you can detect it from 80 kilometers. And small UAV, I doubt that you will saw this small UAV from 80 kilometers. So it is not true. So range depends on configuration, and usually see there more parameters. So this information is that, okay, I can detect target up to 80 kilometers that have radar cross section 2 meters square with probability, and be careful, there is also probability of 80%. Of course, if you want to detect UAV, it is not for detection of this small target, but like example, I can detect UAV up to 5 kilometers with RCS up to 0.1 with probability 90%. So range is always also how you can see variable, because it depends on size of targets and on probability. You want higher probability, range will be lower, of course, because you need to be more sure that this target. Because still remember, we get reflection from anything. So any surface that influence your received signal, and then of course it could be hidden, it could be mass, and so on. What is antenna parameters? Antenna gain 44 dB, decibels. It is dual beam antenna. You can see that there is one beam and a second beam. It is for long and short ranges. So this radar switching, like there is some special modes, and always check long distance, check short distance, long distance, short distance, or different parameters. Of course, I don't know, it is programmable, so you can change it some of these things in parameters. Or you can switch to mode that, okay, I am interested only in long range, I am interested only in short range, and so on. And this radar has two long and short pulse. Also, this is polarizer for suppression of rain reflection. It is very important because you will be surprised how weather can influence range of radar. Because it will be really big storm or snowing or something like this, your range from 80 kilometers will lower to 20, 30 kilometers, because reflection of snow it could be really high. So if somebody told you, okay, we have perfect radar up to 100 kilometers and don't provide any other information, start be suspicious. There is second example of weather radar. I put it because it is typical for primary radar system also. It could be 2D, 3D. It is very well known company Vaisala. I think that is from Sweden or some north part. I think that's Sweden country. It works on C-band. So you can see frequency is from 5 up to 5.7 gigahertz. Why use different frequency? Because this frequency is suitable for measuring of like atmospheric artifacts. It is better. If you will go to higher frequency, then mean that wavelength will be shorter, and you get reflection from like smaller objects, and then your signal don't pass through like snowing or something like this. Coverage is about 300 kilometers, so it is big coverage. Range resolution is 75 up to 300 meters. And again, you can see depends on length of pulse, long, short. So it is one of parameters which we discuss later, and it is very important. Azimuth coverage 360, of course it is weather radar, so we are interested around all of us. Azimuthal elevation resolution is about lower than 1 degree. Okay, and distance. Resolution depends on distance. Up to 50 kilometers is about 1 kilometer. Distance at 100 kilometers is a resolution almost 2 kilometers, and distance at distance 250 is 4 kilometers. Why? Because resolution cell, if you can imagine, it is one cell, classic cell. It is not constant everywhere, because if you are far, it is go to wilderness. So it is clear that if you will be increase range, the resolution, how to say, decrease, because resolution cell is bigger. And Doppler resolution depends on PRF. It is pulse repetition frequency, you will see later, is plus minus 16 up to plus minus 64 meters per second. Why we need Doppler resolution in this range? Speed of wind. Of course, if you will have some low speed wind, high speed wind, because if you check weather forecast, always they saw also what will be speed of wind. It is from this type of radar. Okay, you already saw examples of that different type of radars, generally different type of any kind of RF service, works in different bands. And we need to discuss what is spectrum allocation and utilization, because spectrum allocation we need strictly follow. Why? Imagine that we have DVB-T and you are watching on your favorite TV series, and now somebody use transmitter on same frequency, exactly same like is DVB-T. What do you think that happens? He will start sending some signal. It is not important which one. And what will happen with signal of DVB-T? It will be sum of both signals. But if I will make summation, I will change amplitude, I will change phase, and what's happened? My television don't understand these signals because it is not DVB-T signals. It is DVB-T signals plus some other signal. So it can't follow format of DVB-T, and what's happened? Nothing. You don't see any screen. And it is same as like if somebody use GSM, what's happened? GSM stop working because somebody stole your frequency band and start transmit on frequency your band. And again, summation of both signals makes that my phone don't understand this receiving signal, because it not will be GSM signal, it will be GSM plus something, and we can call it noise, and stop working. So now I think that it's really clear that we need follow strictly rules where I can transmit. And imagine what it mean for us. Now you won't discover some influence of wind turbines. You can't just make design measurement chain and go to place and start transmitting. You need permission. Without permission, if somebody catch you, oh, it will be really, really big fine, because you stole somebody frequency that pay for this frequency. So you need to be really careful about this. Okay, so signals we could divide it to two base category: band limited signals and UAB. ULB is mean ultra wide band signals, and it is really high, huge bandwidth. I will not care about this type of signals. We will take care about band limited signals. And this is example of frequency allocation table. It is from 3 kilohertz up to 300 gigahertz, and each area means some, how to say, reservation for some service, but not for individual service. But this is like radio navigation, this is for broadcasting, this is for also broadcasting, there is for FM radios, AM radios, DVB-T, and so on and so, radar, sonar, I don't know, for like example for some mobile communication is there, mobile communication is there. And it is clear, if like your GSM operator have some part from this bandwidth, then it is reserved for him and he pay big money for reservation. So if somebody just start transmitting on same bandwidth, whole GSM network stop working, and what's happened? Some special authorities will try trace you who transmitting illegally, and you will definitely go to jail, or fine will be so big that you will be surprised, because they pay big money for this reservation, so of course they are very careful about this. Okay, frequency allocation and utilization is, how to say, managed on world radio communication conferences, and they decide, okay, in this frequency band we will use for radars or for radio navigation. This frequency band we use for something else, some other services, and it is worldwide. But of course that then is divided to some small part. Then we have national agencies, because for me it's not important if in your country somebody transmitting GSM signal in some frequency. Of course in Czech I can use it, this frequency band. Why? Because we are so many thousand kilometers far away that it is not important. So then each country like operate with this frequency, handle with this frequency independently. But it is like global point of view, country point of view, and then even in your case like state point of view, because of course if country Tamil Nadu they use it some frequency, in Assam it's not important, it is also long distance, so why not, they can use it. But you understand this mechanism, this control mechanism. I think that this is enough, and I will show you frequency band of radars. Radar system generally are grouped into commonly used bands, and there you can see which band use radar. Usually we use L band, S band, C band, X band and KU band. I will take care mostly now about C band and X band. C band, it is about C band. It's from 2 up to 4 gigahertz. It is for precision landing radars. Then C band from 4 up to 8, and very important is for us X band from 8 to 12 gigahertz. So this frequency is mainly used by radars. Then we have automotive radars, and what you need for automotive radars? Really huge resolution, because you want to detect pedestrian, children, I don't know, dogs, anything, something really small. So it is clear that if I want increasing resolution, I need increasing frequency. So, and for this reason, automotive, it is in bands about 40 up to 70 gigahertz, about 75 gigahertz, I think it is automotive industry radars, because they have big resolution. But what is mean for range? Very short range. It will be up to 200, 300, 400 meters only, because anything it is depends on wavelengths, and wavelengths depends on frequency, of course. So it is clear how to say relationship between this one. So I will try check. Okay, meteor radars, it is in KU, it is from 12 up to 18 gigahertz. Then we have battlefield radars, police radars, and so on and so on. But I think just remember, for us is important L, S and X band. This three is very important from point of view radars. There I make repetition of these slides because I want to give you now more information on this. So this is typical blockchain of monostatic radars, where TX means transmitting site, which include waveform generator. Later you will see what is waveform generator. Generally, how looks pulse? It is just amplitude modulated wave. It is just rectangular. It uses some special kind of modulation, and so on and so on. I think that until present days could exist 50 different kind of modulation, or combination is almost unlimited. So it is depends what you want to detect, which resolution you need, what is, how to say, what is, of course, you know that military radars you very often want are resistant against jamming. Why? Because they use special type of modulation that is resistant to this kind of jamming. For civil, we don't use this special kind because we don't need it. So it is waveform generator. After we generate waveform in TX, that includes pulse shape, carrier frequency, modulation, if it's LFM, so linear frequency modulated, non-linear frequency modulated, or coded modulated. Maybe you know Barker coding, and some other type of coding. I will show you also later. So then waveform from baseband is modulated to your to carrier frequency, because of course we are transmitting on carrier frequency, and then is fed to the transmitter. Transmitter is typically high power amplifier, because you need big power, because you want to illuminate big area, and you know that like your power decreasing with r squared. So it is mean your power increasing very rapidly, quickly to 0. But you want to detect, remember, target up to 80, like example, kilometers. So 1 divided 80 kilometers square, it is really big attenuation. And imagine that we have like long range radars up to 500 kilometers. Is it clear that these radars will have low resolution because they need work on much lower frequencies, because the attenuation will not be so bad. So again, this is first relation. Then from transmitter TX we go to duplexer or circulator. I already described. It is protection of receiver, because when I transmitting my high power pulse, this is unconnected, this part, because if this high power goes to receiver, it will be completely destroyed. Why? Because receiver handling with receiving signals, and when it will be 1 billion times slower in amplitude than my transmitting power. Almost it is hidden, information about targets is almost hidden in noise. So this must be really, really big sensitivity. So of course when I transmitting, I disconnect it. When I listening, receiving, I connected this part and disconnected this part. So it is still switching in pulse shape, how we will see later. Then we go to ADC. Usually, of course, in receiver and in receiver side, first what we need to do is amplifying of my signal, because it is so low that I can recognize anything in this type of signal. So I need really good amplifier, analog of course, with really low noise number, because I want the lowest influence of my received signal. Of course, and if my amplifier will be low quality with some noise, then will influence my signal, and I lost all information about target. So, but it is maybe your area, because I am more signal processing guy, not analog processing guy, so it is more for analog processing people. Then there is some filtration, because your receiving signal has some bandwidth, and I of course make limitation to bandwidth of interest. So there is some few things, but not important for out. It is important for designer of radars. Then we go to ADC converter, and there is clear message. There we stop analog domain and start digital domain. And IQ, it is mean IQ samples of my signal. So I make sampling. Of course, I need full thing, sample theorem, and all this thing that you know for sure from your studies. It is very well known. And I produce complex sample, I and Q sample. Why I don't work only with amplitude, but I work with amplitude and phase? Reason is clear. If I have only amplitude, I have information only about distance, because it is time delay. But if I have phase, phase is frequency, and frequency is speed, and speed is velocity of target. So I'm both, of course. If you are interested only in range, okay, just work with amplitude, it will be simplified. But generally, you want information about your target, especially if will be some enemy, you want to know how quickly speed up to your side. Then we go to signal processor. Signal processors make a lot of function. I can call it pulse compression, Doppler processing. It is include MTI and MTD filters, the moving target detector and moving target indicator. Generally what is mean? MTI filter just removes everything from your signal what is not moving. So the reflection of environment. I don't want this information in my signal, because I am interested about target. And what is MTD? Moving target detector. And imagine MTD, it is bank of filters. So it is like parallelly you have 5, 10 filters. And first filter detect targets that have speed from all like 10 km per hour to 20. Second filter from 20 to 40, from 40 to 60. You get my point. And you like to input to bank of filter is placed your IQ data, and of course only through some filter will pass, because other filters will attenuate, because every filter is designed for specific speed range. Like example, like this one. Then our preprocessed signals, we call it like primary processing, go to data processor. And there, why I divided signal processor and data processor? Because signal processor, we are working with samples. It is signal samples. But after this, we work only with data. And what is mean data? It is detection in this range, or it is not a detection. It could be easily in this range, cell range of my radar is target 1. It is no target 0. It is data. It is different type, but it is data. It is not anymore signal. Then in data processor also we build plot, tracks, and so on, because we are not only interesting where is target, but what is kinematics of target, how he moving quickly, he speed up, slow down, where he go. So of course you need to follow your individual detection. And around this system we have built-in test equipment. It is for checking the health of your radar system, if I can say easily. And power supplies, of course, power supplies, you need electricity. And antenna gear, it is for a rotation. So, and last one is communication, and it is communication interfaces, because your radar usually don't work standalone, but it is connected to some higher system, because of course you will send information from individual radar to some headquarters for fusion of data, because they need information about the whole picture, about the whole situation. So it is something like this. So, is it clear? Can I continue? Thank you. And now we pass through individual things about measurement of position, slant range, and so on and so on. So imagine we are not work on Cartesian coordinates system, but we are working on spherical, always. So you need to think how also convert this information to Cartesian, because what I want to see, I want to see map and where is target. But it is not so easy. Imagine that you have two independent radar and each one work in spherical coordinates. But these two spherical coordinates, imagine that is 1 and 2nd radar, and there is target. For this target, it could be 12 kilometers, for this target 5 kilometers. How you can connect together? It is same target, and you get two different range. Of course, you are working in two different spherical systems. So fusion, it is really complicated thing. It is not easy, because for one radar it is one radial speed. For 2nd radar it is different speed and different range. It is completely different independent value, and it is produced by one target. And now imagine you have situation around Delhi airport where will be, of course it is secondary, so they have information from ADS-B, but if stop working, they need to use information about primary radar. And now imagine situation in your area of interest, if it is 50 targets, and you are completely lost almost. And you have 3 radars, and you need to make combination of 50 targets and always found 3 measurements from individual radars and how to interconnect it together. That correspond only to this single target. It is a lot of combination. 3 up to 50. And you need, and only 50 of them is correct. Rest is mistake. So it is also very interesting task, but it is more for mathematician, because this optimization is really hard. Okay, so, okay, I will continue. This is azimuth, phi, and this will be elevation in 3D, how I feel. And this we call it slant range, and this is x, y, and z. There I just show you brief formula how you could recompute from Cartesian to polar coordinates to spherical coordinates. Just so also is slant range, we call it R. It is clear that azimuth range is from 0 to 360, because you can see circle. It is clear. And elevation is angle over equatorial plane. It is from 0 to 90 degree. So I think that is clear. What we all, if our target is in move, then we measure also Doppler frequency, and based on Doppler frequency we measure radial velocity, not like classic velocity when you are driving car. It is radial velocity. Be careful. It is not the same. Okay, and now what will be interesting for us is And what is precision? What is ambiguity? How you will see, and what is resolution capability of our target position measurement. So, can I continue? Clear? Thank you. Sorry, I always ask for confirmation because it is much better if you have question I can answer if I know answer. So about range measurement accuracy. So how I say, we have slant range measurement. Slant range measurement is based on a received signal delay measurement. So it is called matched filter output, and I will later call it also mismatch filter output. But now matched. What is matched filter? It is filter that give you best, how to say, best results for signal to noise ratio, and it is based on cross correlation. So what is mean generally? I take my transmitted pulse in a specific time, I waiting for received signals, and I might make cross correlation of both signals. And of course somewhere will be maximum. It is like example, if you have rectangular pulse, just pure rectangular pulse, and make cross correlation, you will get triangle. Is it clear? Because you start moving and it is increased. When it's just this, it is this maximum and just disappearing. So cross correlation told me what is mutual area, how to say, and my maximum is in some specific time, and it is my time delay that I need to find. This is example of a cross correlation of matched filter without compression, so it is just rectangular pulse. If we will make some compression of filter, I will later show you what is it. No, it is after compression. Sorry, it is without compression, and this is after compression. So this is just cross correlation of rectangular pulse. Sorry, I made mistake. And this is spectrum of pulse. And you know probably from Fourier transform that is since function sine x divided x. So since you call since, yeah. This is main lobe. Usually we need 3 dB main lobe width, and this is side lobe. Of course, what we want, that energy of this is same like energy included in this, but what you need for best resolution of based on best resolution and minimal error in accuracy, what do you need? It will be this slimmer and slimmer and slimmer, it will be better. Why? Because imagine you have two targets that is 200 meters far away each other. It could be hidden that it will be like interconnected, just two sines x function, and it will be one wild main lobe, and you think it is one target. No, it is two, but you don't have enough resolution. So for me will be best if will be this zero, and whole energy will be in one very narrow peak. It is mean better, higher resolution, I can recognize two targets, and it is based on this. So it is main lobe, side lobe, and now how we compute this time delay. Time delay is of course 2r divided c speed of light y2, because one way and second way, so it is clear. So slant range is computed like my delay multiplied with c divided 2. Easy. What is range measurement resolution or accuracy? It is approximate formula. It is not exactly like this one. It is delta TD. It is differences between two like samples, targets exactly. It is 2dr. It is resolution in range divided c, and I could convert it to this one. Okay, if I will use after compression and only rectangular pulse without any inner modulation, then this time delay is could be evaluated like plus minus 1 divided b. So what is b? It is bandwidth of main lobe. So range resolution depends only on one thing: bandwidth of your pulse. Only on bandwidth, not, and be careful, not on length of bandwidth, only on bandwidth. So it is clear I need more and more bandwidth to get slimmer and slimmer, or higher and higher resolution, it is better say. Okay, I will.
Side lobe ratio, what information will give?
Yeah. Okay. It is about energy, because you want all energy that will be in your main lobe. Why? Because detection you provided by this main lobe, and side lobe ratio, it is ratio between amplitude main lobe and the lowest and the highest side lobe. So it is mean that you want this ratio to be so highest, because then it is mean what? If this will be like only this one or this one or this one, it is mean more and more energy in main lobe and low energy in side lobe. So this ratio you want to be to highest. And why? Because imagine that also there will be some noise. This is without, of course, noise. It will be something like this. And if this ratio will be low, then the main peak could be hidden also in noise. So generally you want this ratio to be biggest. And for this reason, unmodulated rectangular pulse is not suitable for radar, and we always use some modulation, because this ratio is about 13.5 dB only. But if you will use some modulation, some special kind of modulation, could be up to 40, 50 dB, even exists some about 60 dB. So it is about this one.
Increase the resolution of the
Not resolution, but it tell you more energy in main lobe, and you want more.
Wide iteration.
Sorry.
To have wide iteration.
Yeah. Exactly. Okay, there is situation about resolution, or from accuracy to range resolution. There you can see that we are transmitting this, and we have two targets in similar position. You can see similar range. You can see that is slant range. It is like on circle. So it is not depend if this will be, I don't know, there. It is still same slant range. And resolution, this is very close target, distance R1 and R2, and this is my resolution. And what will be result after matched filtration? I will get something like this. I can still recognize. But if this will be lower, you will see one big main lobe, one target, or two targets. So I think that message is clear from this one. And imagine that you have more and more targets. It could be more and more complicated to get all this information. Yes. So again, be careful, resolution is set by bandwidth of target. Why bandwidth? Because it is this one. If will be generally bandwidth higher, resolution will be lower. Can I continue? And now range ambiguity and its resolution. I honestly must say that I have little worries about this part because it is not much easy. And I will try to explain. Imagine we are in time 0 and I. Just forget about this one now, for now. And I transmit pulse. It will cost 1 microsecond, I don't know, some period of some time. And what I doing now during this time, like during this time, waiting for response, for response about target. Is this target, not target? And I get this response. Just forget about this one. Okay. But I am not sending one pulse. I will send pulse every half second, every 100, no, not, it is not true, every, I don't know, 100 milliseconds pulse. And now imagine, I will send this one and get this one. I will send, after this time, I will send this one and receive, this target is stable, don't moving, and it is still same position. And get this one, I will send this one and this one. So it is transmitted pulse. And now, how you want compute range? You will tell me, yeah, this is this time delay and I will compute range. How you can be sure that this answer is from this pulse and not this pulse? Yes. It could be close target or this target. And this is ambiguity. And this is, you get my point. It is not easy. Imagine you are sending pulses and getting responses, but you need to be sure what is ambiguity range. And after you will be in higher, like in outside of this ambiguity range, you will receive better response. So imagine my target is 60 kilometers. Of course, this is time delay, but I will recompute to range. But I can identify this target like target that is 5 kilometers far away from me. And you will be surprised. No, he's 60 kilometers. But my radar told me it is 5 kilometers. And it is wrong. So it is clear. I think that this is clear. There I need to be extremely careful because I can't listen for answer very long time. Only to some maximal time delay. Why? Because then I start transferring transmission of new pulse. If you get my point. And then again. In tutorial I will show you this one about ambiguity range, how to compute, how to deal it. And is it clear? Can I continue? It is clear why this is ambiguous target, because I don't know if it's this or this. So imagine 60 kilometers, 5 kilometers, but true range is 5 kilometers. Measured range is 60 kilometers, but measured is 5 kilometers, but real is 60 kilometers, like this example. And how you can avoid it about this? This space between transmission of individual pulse every 100 milliseconds, like example, we call it pulse repetition interval. You will saw it maybe 1000 times in my presentation. I will call it PRI, pulse repetition interval. And inverse value of pulse repetition interval is pulse repetition frequency, PRF, because sometimes it's for us suitable work with PRI and sometimes with PRF, but it is just inverse function. So how we can avoid this ambiguity? I will make higher interval between transmission pulses. Is it right? Yes. If I will wait longer time before I transfer second, like example, this node will be there, but I will send this and then this, then will be okay. It is unambiguity. It is okay. It will be clear message where is target. But I tell you that is not possible. And you know why? If I will do it, I will get higher unambiguity range. It is true. But due to this, I will completely destroy resolution in Doppler. So you need to choose. You want good unambiguity range, then you will get really bad resolution in Doppler, so you can't recognize speed of targets. So it is leveraging. You need to be really careful about this one. And remember short long pulse about that I show you in real radar. It is about these ambiguities. So we use different regime, different these things because we can handle it. So it is about this one. So okay, I can improve. Higher PRI. Doppler will be destroyed, how you will see later. Because Doppler is computed from individual pulses. I will show you. There exists one tool how we can handle it, and it is called staggered PRI. What does mean? It is our classic situation where is non-staggered PRI, fixed spacing between samples, everything is clear like on last slide. But ambiguity target. But if I will use staggered PRI, and what does mean this? That I transmit like staggered PRI, that I transmit pulses, but not always in the same time. Imagine, first I will send in some time, and then not constant constant gap between two pulses, but second pulse will be slightly shifted, time shifted. So what does mean for me? From first pulse I get ambiguity range, from second I also get ambiguity range. So I have two wrong ranges. Why help me? Because by comparison of these two results, I can find solution and exact value where is my target. And it is called staggering PRI, staggered PRI. So there is some slight shift. Imagine it will be 1 millisecond and 1.1 milliseconds. Well, it is like jittering in pulse. It will be, of course, in specific times values. It is not random. It is like, it will be like moving like in time.
We received the number of samples is more than at that time, and we have compared the both and after.
You compare like both results from time delay. So you have like, in my example, you will see that you have like one ambiguity, real target will be in 210 kilometers. But my detection of this will be on 60 kilometers, and always you will receive 60, 60, 60, 60, 60. But it is wrong value. But from this case, with staggered, you will, from first pulse, you will receive I don't know, 150, and from second, slightly shifted, 120 kilometers. So I have two bad values, but due to one equation I will show you later, we can solve this problem, and result will be okay, my target is 60 kilometers far away, or I don't know, some value that is correct. So it is so-called staggering, and very, very often is used almost in all primary radar systems. And why I talk about this when we talk about wind turbines? It will be close. For me, it's two targets, and it could happen that will be masked. It's the same problem, because what is reflection from wind turbines? It is target. And how we call it, you have two different type of target. Target of interest, that I care, and target of non-interest. And what is non-interest? Everything what is not interest. It is easy, just opposite. So, and I must say, target of non-interest is definitely wind turbines. It is clear. There is little advantage, because if you place a target to some environment, of course, what is advantage of wind turbines? They are not moving. I mean, change position, they are static. Unfortunately, they have blades. And this causes our problem, because if will be only tower that is not moving, I will just use MTI filter, moving target indicator, and just remove it, this clutter away. And if will this happen, I will not have lecture on IIT, because it will be easy solution. But of course, this blade causes Doppler shift that is really in similar values like Doppler shift of my targets. Because you will be maybe surprised, but if you have blade about 80-90 meters and rotation speed, I don't know, 9-10 RPM, then on the tip and the end of blade is rotation speed about 800-900 kilometers. And it is speed of my civil of my civil plane. Okay, can I continue? And now I will show how to solve this, but just it is easy, don't worry. And I also all program on my MATLAB, so you can just easily use the script. So true time delay of target is true, tau true is 2 multiplied with this slant range divided C. Unambiguous range depends on pulse repetition interval. So it is C multiplied by PRI divided 2. It is clear, because it is length of this interval divided 2. It is maximal unambiguity range. But if my target will be far, I am outside of this unambiguity range, and we have problem. We need use to stagger. But my measurement is tau true modulo PRI. Why? Because everything is shifted to my PRI, like aliased, if you understand me, always to base interval. So for this reason, imagine if this correspond time delay, true time delay 200 kilometers far away targets, but my PRI, my unambiguous range is defined by PRI, is shorter, then this time delay, my radar C modulo PRI by some value, so result measured time delay will be much lower. And what does mean? Okay, I will see target that is in slant range that is closer to me, but it is not true. So it is just modulo PRI always. Delay to range, okay, if I will recompute this one, and of course I will work with slant range, it is again, it is what I measure,
what is true modulo unambiguous range. It is still same, but it is just conversion from time delay to slant range. But it is, you can see it is same. So how to recover? I just put this formula. Later during tutorial you will see more in detail because it is not necessary. We need to solve this equation. We need to find n1 and 2 to be correspond this equation, and if we will found it, result is true range. And later I will show you with exact values and we will compute. You can test it. So, is it clear this one? I don't know how we can handle it. We are on slide 14 from 80. Okay, I will try speed up. Azimuth measurement. Generally, azimuth measurement works in a way that is really quite similar to range. But now for us is antenna angle where you are looking. And what is depends resolution, of course, on my antenna pattern. Be careful, it is this not spectrum, it is antenna pattern. So where is radiation, maximal radiation of my power is in main beam. And we are take care always not about this maximal value, but minus 3 dB. So this is definition of my resolution in azimuth. And again, what you want? Slimmest, narrow, thank you. Narrow will be better because I can easily recognize. And this we don't want, we want 0, but it is not possible physically, it is theoretical only. And this causes us, this side lobes of antenna cause it very big problem. Why? Because I can detect target by this. But this is different, it is angle. So I get wrong azimuth. So we are not take care about maximum. Why? Because maximum can slightly movement. It is depends on many things. So we care and 3 dB width of main lobe. I think that I will continue. And there is just a list of azimuth measurement influencer. What everything could like make me problem with in azimuth measurement. It is pole-to-pulse fluctuation. What does mean? You transmitting pulse in specific times. But this is not true because there is some oscillation of pulse to pulse because you never have absolute value. Frequency agility, because you use like carrier frequency 10 gigahertz. No, your oscillator is not so stable. It not will be always 10 gigahertz. It will be plus minus some hertz. But again, it is wrong. It causes your problem. So pulse-to-pulse fluctuation impact on azimuth is jitter of detected maximum, because I don't know where is exactly maximum of antenna beam. And for this reason, I don't care about maximum 3 dB beam width. Frequency agility. So again, carrier frequency is jitter. It is biased or jitter due to spectral RCS variation. Again, jittering. It will be, you don't get exact value. Also, I am sending pulse with some amplitude. Amplitude is not stable. It is not constant. Again, it will be some jittering, something like this, because I can't make so high, like infinite stability, of course. And it will be some random or systematic offset, and then flag maxima, low slope, it will be high sensitivity, a large error, but it is not important. So it is this 4 azimuth measurement influences. Okay, what about height and elevation measurement? Height and elevation measurement, it is not easy with single beam antenna, but this is based usually in 3D radar with multiple beam antennas. What this means? That I have no one beam that transmitting, but multi-beam. And from comparison of the results, like imagine, one beam is this, one beam is this, next this. So I get like measurement from different beams, and then of course I can evaluate elevation. Multiple beams properties, higher gain, easy installation of multiple transmitters, lower sensitivity to meteor clutter, low precision. What about height? Or height? How is your pronunciation? Height? Height. Sorry. Height, I am not native. Height. Usually we use it some barometric height measurement readout from SSR. What is SSR? Secondary surveillance radar. It is radar that is, it is devices that is placed on plane, or we can use GPS information about height, ADS-B, and so on and so on. So it is height and elevation measurement is based on this one. It is important, especially of course for air traffic control. So, what about radial velocity measurement? How I say radial velocity measurement is based on Doppler shift. There is interesting graph that told you all this information. Imagine on axis X we have PRF, pulse repetition frequency. It is inverse value of pulse repetition interval. So if will be pulse repetition interval longer, it will be shorter frequency, of course, and I have a higher unambiguity range because it is longer period, but it is good. So you can see it is this curve. So for 1 kilohertz it is mean 1 milliseconds, 2, 3, 4, 5 up to 10 milliseconds. I have unambiguity range 150 kilometer. So everything under 150 kilometer I perfectly detect like slant range. Good. But what's about radial velocity? Unambiguous, because it is so same. It is same principle. Lower PRF, lower unambiguity range. So it is against, it is just opposite. It is bad. And what this mean in reality? Imagine velocity based on measurement of Doppler shift. If I will have carrier frequency like 5 gigahertz and 10 gigahertz for comparison. If I have 5 gigahertz, then it's clear that due to motion of my target, my velocity caused some Doppler shift. And if will be lower, this PRF, because it is connected with this PRF, if will be lower value, then this, how to say, velocity of target caused lower Doppler shift. But if will be lower Doppler shift, resolution of this velocity will be bad. So for higher frequencies will be better. So from point of view radial velocities, resolution and detection, I want highest PRF is better. But if I will use 10 kilohertz PRF, my unambiguity range will be 12 kilometers. If I will use 1 kilometer, one PRF. Unambiguity range will be 150, but on 10 gigahertz I even can't recognize it is under 0 because I can't recognize of movement of target. So it is like two things that go against each other. And again, you need to make some leveraging, something like this, of course. And it is really not easy task. And so this is clear. This is on this axis Y. It is slant range, maximum unambiguous ambiguous range, that decreasing with PRF. And on opposite, there is speed of targets. And radial velocity ambiguous is definite for always. Of course, it is independent on carrier frequency. For each carrier frequency, of course, you have different lambda, different wavelength, and it is correspond to different line. So there is unambiguous, yes, there is no. So it is like you have two axes Y. It is a little confusing graph, but I think the message is clear. If you want this good, this will be bad. If you want this good, this will be bad. So you need to be somewhere in this area, of course.
Sir, Doppler we have used in the previously we see the transmission and the receiver end.
Where?
Doppler.
No, Doppler.
Used in the receiver and transmission.
No. You transmit. You are transmitting pulse. It is just some modulation in some frequency, carrier frequency, but Doppler is only on receiver side, because imagine if you are transmitting something, there is no Doppler. It is just high frequency pulse. But this high frequency pulse in 10 gigahertz just hit target, and due to this hit target, due to movement of target, this carrier frequency will be shifted by Doppler shift. So it not will be 10 gigahertz, will be 9.9 gigahertz. And from 100 kilohertz difference, I can compute speed of target. Oh, sorry. I can compute speed of target. And this tell me what is maximal speed that I can detect. So it is like this connection. Again, there is radial velocity measurement if I have low PRF, high PRF, or medium PRF. So low PRF, unambiguous range is large, good. Doppler velocity ambiguous, low. Good for long range surveillance, poor velocity measurement. Vice versa, high PRF, it will be completely. So we are operating in medium PRF. And unfortunately, both partially ambiguous, because you need to be careful. And honestly, this is not easy task, and a lot of radar engineers leveraging what is better. And of course, also depends on purpose of this radar system. What is more important for you? What is more important for your client, customers? Okay.
Depends your output.
Yeah, what you want. Yeah, exactly. But this is used in practice. And ambiguities, even for range and for velocity, is based in signal processing, and you just remove it by solving this one equation.
So what if we use separate transmitter and receiver, and their ambiguity will be removed and all things, like separate transmitter for
Yeah, it will be bistatic.
then this problem.
I don't have board there, but bistatic combination is always triangle. Imagine transmitter, receiver, target, and now you are in big trouble, and I will show you transmit, reflect, And imagine, you measure bistatic range. It is not slant range. And where is location of target? It will be ellipse. And where is located in ellipse? You don't know. Because it is this plus this is one value. It is what you are measuring. It is this range. But it is ellipse. And results will be still same. So you need to have minimally 3 transmitters of opportunity, and from cross sections of all ellipse you will define where is target. But can you imagine how many cross sections will be there from 3 ellipse for one target? 2, 4, 6. Okay, one target. And if you have 50, it is billions of combination. And you need to solve, okay, which is right one? I make PhD on this. It is not easy task. It is really billion of combination. So stay in monostatic. No, I joking. But in bistatic is not using like in air traffic control. Or if exists, I don't know it honestly. I never saw it.
Sir, why don't you typically combine I have always seen that in time of arrival or any method we mostly use the range measurements, but very often we avoid the angle measurements. Angle measurement is also there, right?
Yeah. Yeah.
But we
It is this azimuth.
If I have bistatic range, angle and azimuth, I can specifically say where it is on the ellipse. No? Because we know that the distance between the transmitter and
But you, yes, but it is only one combination receiver and transmitter. But then you have same transmitter and other receiver. Same receiver and another transmitter. It is completely independent. So all combination is completely independent in bistatic solution. During break I can just draw you picture that is not so easy, because always you get triangles. Transmit, like receiver, transmitter 1 and target, triangle. Then you have one receiver but another transmitter, and it will be another ellipse. So another bistatic range and another bistatic range, another bistatic range that correspond to one target but 3 different values. And now imagine you have more targets. How you can know that this 3 range correspond to this one target? You don't know. How you can choose it? You don't know. It is completely independent. So you need to compute all combinations. Believe me, I can send you some more information about this bistatic measurement, but in bistatic generally it's more and more complicated about this one. It is not so easy. Okay, and about ambiguity of radial velocity, this is visualization of blind speed. You know that in range we have ambiguity range, unambiguity range. Unambiguity, it is range that I can perfectly detect what is range of my target. After this is ambiguity range, because I can't be sure, of course, because I get a bad value. Exactly same working in ambiguity of radial velocity measurement. And why? Because you know, like example, in this example, if we have like carrier frequency 10 gigahertz, wavelength is 3 centimeters, PRI is 1 millisecond. So first blind speed is 15 meters per second, about 54 kilometers per hour. And what does mean this blind speed? Why occurs this blind speed? Because it's divided. It is important with, it is connected with PRI. So if I will compute speed of target this, then if my target will move by speed doubled, tripled, and so on, for me same. It is depend on wavelength. Look, it will be, I can distinguish stationary target from targets moving at multiples of half of the wavelength during the repetition period. Look, it is 1 µ signal, 1 µ pulse second, and so on. It is different pulses. And this is moving target responses. If it will be shifted about half of length, I will get this result. This, always same. So it is mean he don't move. But if not will be about, it will be different value, you can see that it changes. It is very, very similar to ambiguity of in range, but it is in speed. So I can say that in speed, we call it this ambiguity, we call it blind speed. Why blind speed? Because all values we don't know that is right, so it is blind speed, and it is all multiplication of first radial speed are indistinguishable. So all this multiplication, and later I will show you how. And removing is in principle completely same like for range. Only I working with speed. And how I can improve and make higher blind speed, because of course I won't detect targets not at 15 meters per second. I want much higher, make higher PRF, and it is mean shorter PRI. And again we are back. It is opposite. Then I have one slide about measurement errors. Which kind? It will be quicker. So we have random, of course, effect of noise. Noise is everywhere. Effect of amplitude quantization. Of course, because I made AD conversion and quantization error, I think that you know it very well in electrical engineering, what is quantization. Effect of sampling, because we are not sample exactly in same time, because there is also jittering. All this random effect I can relatively reduce by impact by averaging longer CPI, better scenario. And what is CPI is coherent processing interval, because I always show you now, okay, we transmit one pulse, receive, one pulse, receive, one pulse, receive, but this causes pure resolution in Doppler. I need better, so I make integration through many and many pulses, not one pulse, but like through area of 100, 1000 pulses. Longer time of integration, it is improving. Okay, if until now is clear, I will continue to radar displays. It will be more interesting. You can see this is 4 base visualization of outputs: A scope, B scope, C scope, and PPI. If we need range only, we can use E scope. What is this? It is just amplitude of my response, and it is clear my target is there. This could be caused by noise or something, or it is weak target. Of course, it could be, but it is range, amplitude. B scope, it is range and azimuth. So you need range and azimuth in one scan, because what is one scan? It is one rotation of antenna. And you are scanning this. After 6 seconds, again I will scan same place, and so on and so on. So you can see in which azimuth. This gives you information about only about range. but I don't know angle. I don't know where is it. I know that it's in 50 kilometers far away from me, but I don't know where. This told me it is 50 kilometers in this azimuth. Then see scope, it is azimuth and elevation. So it is in azimuth and elevation, so I win exactly in 3D where is it. And PPI, it is range, and it is like this movement. Okay, and now we will go for animation. I prepare. You can see this is azimuth. What is mean this free? Static target, it is reflection from building, something what is not moving. And what is this? It is something what's moving. And it is far, far away from me. So amplitude decreasing because lower and lower energy. Is it clear? It is useful this for calibration or clutter studies or something like this. Then we have B-scope. Again, free static target, and one is moving, azimuth and range, so you can see how it's move. By the way, this is not from real radar, it is just my simulation, but it looks very, very similar. This is C-scope, so azimuth and elevation, so you can see just for one target. What do you think? What is disadvantages of this C-scope? Look at the axis. Okay, I know, azimuth, elevation, so it is clear.
Distance.
I don't know how far in this. Exactly, good point. And this is classic radar display. Probably you know it, this display. Exactly. Plan position indicator, PPI. Exactly. On other slides, I have examples from real radars from my friend that previously working in a radar company, so I will show you some real looking data. I think this you can see range, because of course position of radar is 0, 0, 0. It is there, so you can see. And what is this? It is your scan and every rotation. Of course, you can also make display of map, because it is like, is it possible to interconnect it? You can see, I don't know.
3D map.
Yeah. 3D, no, like 2D, I think. Like classic, if you have seen map of airport, around airport, something like this. 3D not, because it is not 3D, so it is not like, how to say. It is like scan, so there is no elevation, it is just azimuth, there is no elevation. So
Connect two types of like elevation and this to make a 3D kind of into exact.
You will see. Oh, okay, wait. Wait for this picture. It is from a real radar.
Yeah.
So you can see it is, what is this? White one, it is tracks. This individual detection in time. There is information, I don't know exactly which one, of course, because I am not working with this. It could be about, I don't know, elevation, height, it could be ID of airplane, it could be anything. It is depends what you, of course, what radar knows about this, how to say. But this is real, like what see radar operator. I don't know if in ATC radars in Guwahati, but will be something similar if you understand me, because every radar has own visualization of targets, but this is classic PPI. This is presentation of B-scope. This is PPI, this is PPI, this is B-scope, and this is visualization of radar system. And why I put this screen? It is in Czech Republic, in Čáslav airport, and this is flat, you can see it. And there is hills. It is not looks like, but it is about 80, 100 meters, something like this. It is flat, 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 and go up like this. And this reflection is this reflection. Hill, it is not mountain, it is. But no, I joking. Yeah, it is like this. So, and this is in B scope, and exactly same information, it is in PPI. It is the same, just wrap it in another visualization. So you can see it is again distance, slant range, and phi is this azimuth. And this is position of your radar. And why do you think that there is some white space? Just guess. It is so-called dead zone of radar. Why? Because imagine, during transmission of your pulse, you can't receive. Plus some extended time. Why? Because reflection will be so strong that will destroy your receiver. So this is blind zoned. It is like, it is depends on many variables I will show you later. You can easily compute, but you understand me. So radar generally has blind zoned. And what is this maximum? It is maximum range of your radar. And there you can't saw it. So if we will have radar up to 450 kilometer, like this weather radar, this will be 450 kilometers. And blind zone will be, I don't know, 3 kilometers, something like this example. But I'm guessing because of course you need to put to equation and compute, but just imagine. So radar never see, never can detect anything what is in blind zone. Why? Because you're just not receiving information, because you are transmitting during this time, plus some amount of time that you will add to this after pulse. Because if there will be some big target really close to radar, the reflection will be so strong that you will destroy your receiver. And we call it blind or dead zone. Okay, I didn't watch time. I don't know. We are okay.
We have a tea break.
Tea break. Okay, so
lecture completed this or still it's there?
no, there is 45 more slides. So should I continue or tea break?
If you have a short tea break, sir, then we can.
Okay, it is up to you, guy. And of course, on online people, so it is up to you. If you want break, we can make break.
Again, we can have right now 3:45 at 4 o'clock again we can start.
Okay.
But
Okay.
you also is there for 1 hour.
Yeah. Okay, so it is up to you. For me, it's not important. I can deliver lecture even in 2 hours in a row. No. I think that is good if we will make a break.
So we can have a strict tea break of 10-15 minutes.
Yeah. So we will come back at 4?
Yes, sir.
Okay, perfect. So go for tea.
We will resume the session at 4.
No, I will be good with water. Thank you. I already have one. Please always stop me because I didn't watch a time. So if I will just make extension because when I start talking, I never stop. So be careful about me.
Sir, please join us.
Okay, thank you. Because I really don't watch, so I can't follow the schedule. So just please inform me. Okay, I will mute it. problem. We are already in delay about 1.5 hours. I need to speed up. I'm still missing 40 slides and we should start tutorial. No, I will now speed up. Anyway, can I ask, you are PhD students, master students? No, I am just asking because I know that there was students from Hanuman and some students from Gaurav, so I am just asking.
We are also from the Gaurav also.
From Gaurav. So it is tough mental. I know him 12 years, so. So, waiting, or can we start? Can we start? Oh, yeah. Thank you. Okay, we will continue with lecture, and now will be about power budget radar equation. On first formula you can see reflected wave-free surface power density. S2 it is received signal, S1 is transmitted signal, RCS is radar cross section. It is something in meter square what is like effective reflection surface of transmitted wave from the surface, from the target, something like this. Later you will see exact formula. Surface power density at the radar antenna is defined by second formula, and after some mathematical changes we could make received power at antenna output or input. It is same antenna, so it is received power of antenna. So you can see that received power in radar depends on many variables. You can see it is transmitting power, gain of transmitting antenna, gain of receiver antenna. Of course, if you use same antenna, GT and GR is same because it is same antenna. Then you have small t square, small r square. It is parameter related to antenna. F up to 4, it is parameter related to antenna pattern. How is designed antenna pattern? But usually this capital F4 we can ignore it and tell it that is 1. It is depends in some small thing. Then is RCS, then is lambda squared, and lambda squared of course it is related to carrier frequency. And what is interesting in denominator is 4p up to 3, r up to 4, and capital L squared. And what is this? It is losses. It is a lot of different kind of losses. You can have atmospheric loss, loss of polarization, loss of free space, and I can continue so on, so on. So generally, what is for us important? This is transmitted power. Okay, it is clear message. Like transmitted power in previous example was 14 kilowatts. Okay, pulse. It is transmitter antenna gain, maybe 20, 34, 40 decibels, something like this. If we use same antenna, it is same numbers, of course. This is antenna thing. I will skip it because we don't have time. RCS. So it is generally area of surface of my reflected surface. So it is important. If this will be really small drone, of course it will be receiver power will be lower, and this we can't influence so much because it is carrier frequency. So if you decide that your radar works in 10 gigahertz, it is for you just constant. This is problem, because imagine 1 kilometer, 1000 up to 4, it is a huge number. Up to 80 kilometers, 80,000 up to 4, oh, it is very huge number. And imagine some radar types where its range 450, 500 kilometers. Can you imagine this number? Very, very high. So what is main message? This is a really small number. You can imagine. And what is interestingness, this is related with signal to noise ratio, because it is clear if my received signal will be lower, the influence of noise will be higher. Clear. So I need this ratio, best one. So what is mean? I want strong signal and low noise. This is Boltzmann constant. It is temperature of system, and it is my bandwidth, and it is related to my transmitter pulse. So it is radar equation. Of course, we usually don't compute receive power in this form, but we make conversion to decibels. Why? Multiplication is just summation, and division is just with minds. It is much better. There you have example. So if you can see this example, for I just try put example, ratio between transmitting and receiving power, it is about 200 decibels. So if you make inversion 200 decibels, and you know that 3 decibels is to half power in linear units. So 200. It is very low number. I'm sorry, I have so many slides that about 2-3 slides I need to skip it. There is an example of received signals level from precision approach radar. So you can see transmitter power is about 100 kilowatts. And in second row you have units in dB, because like radar engineers we work more in dB than in classic units. Because why? Because difference between transmitter power and receiver power is so big numbers that these numbers will be huge, extremely big or extremely slow. So dB is much more better for us. Antenna gain, how I say, about 40 dB. Antenna radiation pattern maxima, if it is 1. Form factor, it is 1. Wavelength, it is 3 centimeters. Radar cross section, evaluation 1 square meter, range 20 kilometer, and received power, if you will make sum of all this, you will see minus 74 dB. It is just example. Of course, for another radar will have another values, but if you are planning like a radar system engineer, which power do you need? You always need compute something like this, some like equation. Okay, I skip it. Then I will talk about range equation, because I already told you briefly. Okay, range equation, what is mean range equation? It is not mean, okay, my radar has range 100 kilometers. It is not sufficient information. Under which condition has range 100 kilometer? And of course, we just make derivation of this, and it is received power must be higher than some minimal power. What is minimal power? If minimal power is power that if will be my received signal under minimal power, my signal will be lost in noise. I can't recognize, I can't detect, I can't process, I can't do it anything else. So I think that is clear. And of course it is received power, so I will use previous power budget equation, and this minimal is signal to noise ratio minimum value. So what is mean? It is minimal value of signals to noise that allow me detection of target generally. And this is multiplication by power of noise. And power of noise is computed by Boltzmann constant multiplied by temperature of system multiplied by bandwidth of noise. Because imagine if I have 1 megahertz and some amount of noise, if I will extend it to 2 megahertz, noise will be doubled. Why? Because it's doubled bandwidth. It is independent. So there, don't think that if you will do it narrower bandwidth, that you will make limitation of noise. Yes, you will limit, but you will limit also your bandwidth. So there is no win-win situation about noise. Noise is always present and always will be in more bandwidth. So if I will compute signal to noise ratio, what is minimum, so it is mean how weak could be signal to still make a detection. It is something like this. It is with pulse compression, without pulse compression and with pulse compression. So you need to satisfy also this condition. So when we talk about ambiguity range that depends on PRI and so on, it was theoretical value. Why? Because it depends only on PRI, but I didn't consider power budget. So it is mean, okay, theoretically I can have it range 100 kilometer, but it is not true. It will be much lower, because I don't add to this ambiguity range. I didn't consider power budget equation. So, and there is some derivation of this equation, and in the maximum of antenna diagram pattern is maximum with considering all things of power is divided by this equation. You need just follow and put all these inputs. I am sorry, I need to little speed up this, but you can just use it. It is in classic any radar signal book, you can find this equation. Now I want to say a few words about reflective properties of targets. So imagine we have impacting wave, and what on which depend impacting phase. We can have it monostatic or bistatic reflection. I will talk only about monostatic. There is important properties, polarization, and how you know we can have three different kind polarization: vertical, horizontal, and cross polarization, that you transmit one polarization and receive another polarization. It is important because when I presenting results from our measurement, I always have vertical, horizontal, and cross polarization. I will show you later that cross polarization almost hidden any reflection from wind turbine. That is not good that we use vertical or horizontal. What is radar cross section? Imagine that is some surface, plane, drone, anything what you can imagine, and reflectex wave, it is square meter and it is angle and it is depends on all this. So it is, you can see it is depends on angle, because of course if I have this object, my reflection, it depends on angle, on any surface, and it is very variable. How looks real radar cross section? Okay, it is on this slide. This is example of radar cross section for one cut. Of course, this is azimuth, and you can see that is very variable. Why? Because plane is complicated. It is reflection from individual parts, and everything is influenced by shape of this target when it's reflected. And what could be values of this RCS, I will come back. Usually RCS, they told you, okay, small aircraft, they have on band 1, 2, 3, 5, 10, 17 gigahertz and so on, they have results of RCS, radar cross section. So it is 2 square meter, 3, 2.5, 5 to 8, and so on and so on. But can you see this result? It is one number. And check reality. Okay, 5 square meters. But it is in average. It does not mean that is true. So definition RCS by one single number is not good, because this is reality. Oh, sorry. This is yes. This is some average approximation. Okay, you can say, okay, this object has about 2 square meters. Yes, but in some direction could have 5, in some direction almost 0, because it is dependent on azimuth, on shape of target. So please, this is a nice example, but it is so far away from reality. It is some average description by numbers. But you see in previous slide, it is very complicated. You even can't compute, you can just measure. For measuring of RCS, if you want to measure like some UAVs or some targets, antenna, what do you want? You need an anechoic chamber, of course. Why? Because I need to remove all any influence of signal that is in environment. I need just a reflection from this one. I don't know, do you have on IIT an anechoic chamber, some big one? Yeah, you have it. We also have it up to 40 gigahertz. So it is like 4 by 5 meters, something like this. So we can measure relatively big UAVs or antenna design pattern, of course, and so on and so on. So check about illustrative figures of RCN in square meters. Insect, birds, it is about 94 dB. Some small plane minus 10, people, and so on and so on. And check this. this reflection could hidden and all of this. Okay, wind turbines didn't hidden racket, but we probably will have problem with this object. So it is clear message that wind turbines is really bad for us because reflection surface is a really big one, and it is 1.5 megawatts. Now I present you that we have bigger one, about 6 up to 8 megawatts. So blade is much huge. So it will be probably go to right. There is some few examples of real radar signal processor, some records. Again, it is from Czech Republic, from Čáslav, and this, maybe it is hardly visible. There is some few lines, colorful. This is clouds, so it was some cloudy. This is reflection from surface, and this is these hills, and again these hills. So you can see this. This is visualization of amplitude, and this is visualization of phase. So you can see why this is black one, because it is static. Why this is not black one, because cloud moving. So it is like this, but there is no target present. There is another example of radar signals where is dark. It is zero Doppler shift, so it is mean static. This blue one, it is departing clouds, and this red one is incoming. Why different color? If something go away from me, Doppler shift will be negative and positive, so it is just different coloring. Okay, now I will go for radar signals. This is my transmitted pulse. Clear. I will not talk about inner modulation. It is just pulse. And this is length of pulse. And there you can see length of pulse plus some amount of time. We call it blind zone. And this is this blind zone that I already present you in this circle. It is zone where after I finish transmission, I can't receive any answer because signal will be so strong that will destroy my receiver. Clear? This is PRI. It is difference between two pulses. It is clear. Inverse value is PRF, pulse repetition frequency. There is instrumented range, and what is mean? It is mean where my radar listening of receiving signal. Why he didn't receive there? We call it dead zone. Why? Because in this dead zone we use it for calibration of radar. We use it for checking of health of radar, for a reconfiguration of pulse. Imagine if this pulse and this pulse will be in some mode, short one, long one, short one, long one, or something like this. I need to switch. So in this time, and I use it for switching and of maintenance, and for all this I use this dead zone. So this is my unambiguity range where I can record my received signal. There is too short, there is too long, if you understand me. So, and of course this is automatically repeated until forever, until you switch down, of course, radar or something like this. So it is like this. So I think there is no more commentary. So this was already present, but now it is in more detail. So we are switching only to receiver part, and generally after IQ data, when we take samples from analog to digital domain, we are after AD conversion. It first will be pulse compression. Pulse compression is cross correlation, I already talked about it. Then is MTI, MTD filtration, I already talked. Moving target indicator, it is mean removing clutter. Everything what is not moving just go away, because it is reflection from environment and I don't want them in my signal. I don't need them. Of course, if you will make SAR, synthetic aperture radar, so scanning Earth, you are interested only in this, so it is different task. But we will state that we will detect moving target. Then we have MTD, moving target detector. It is bank of filters where each filter detects specific range of velocities. And how looks like? What do you think that will be? Which type of filter from the main for, you know, low pass, high pass, band pass, and all these things? So what do you want? It is band pass filter. Design it for specific Doppler shifts only. It is nothing else. It is not. It could be complicated, of course, this filter, but in generally meaning it is not so bad. Then is detector. And what doing detector? Imagine that I always talk about radar cell. So it is mean radar cell is resolution cell 1 by 1. And it is about detector. Detector told me is in this range, and in Doppler it is present target 0, 1, yes, no. If no, I don't care. If yes, I care what is type, and I move in next operation. So imagine like a grid, divide it, and each cell you just checking it is there, it is not there, it is there, it is not there, it is there, it is not there, and so on. Then is, okay, it was integration, then is detection, and there is CFAR. It is constant false alarm rate. Okay, it sounds honestly, but what is it? It is mean with which probability is in this cell target, because I can set it constant false alarm rate CFAR on constant value, and if amplitude of my received signal in these cells will be higher than threshold, there is target. If it will be under threshold, it is no target. But this will be very influenced by environment, because in some cell could be low reflection, in some high. So we usually don't use this CFAR like constant, but we call it adaptive CFAR, because it is adaptation to your clutter, to your reflection that you don't want in a signal. So it is CFAR. And then is coordinates extractor. What is mean? Extraction coordinates, it is mean, imagine you have mobile and now radar, and first pulse hit this and reflect back to radar. Second pulse, third pulse, fourth pulse, and so on. So I have 5 reflection like example, but all correspond to one target, my mobile or UAV or big plane. So I need to make matching of all mutual detection that correspond to one target, because you don't get only one reflection per target, but you will get multiple. On which one depends? On how quickly you send PRI and size of target. And then you need to make some analysis how make the cloud of point reflection to one object. You need to make some decision. Maybe you know DB scan method that take clouds of point reflection put together or something like this. So it is target coordinators. Generally, radar signal and data processing we divide it to three parts. Primary, it is pull compression, Doppler filtering, target detection. So their target detection is this target, it is not target. Then secondary processing, it is target tracking. So if I know after extraction, I know coordinates of targets, okay, there is target. I am interested in secondary processing. If this target is moving, where will be after 1 second, 2 seconds, 3 seconds, 4 seconds? So what is target tracking? Just showing where is my target. So it is individual detection, extracted coordinate system that show me on map. And there also is including additional information. So if my target has a ADS-B, I know what is type of target. I know height of target on the ground, and so on and so on. Then we have tertial processing, and it is about data fusion. If you have multiple radars, because imagine if you have multiple radars, distance, speed is relative value. It is only depends. It is only valid to one radar. For second radar will be different distance and different speed, because it is depends on movement of target. So it is clear that you make on some logic fusion and tell him, okay, this target with this range with this speed correspond to this target with different range and different speed. Because why is different these values? Because it is different mutual position between two radars and this target. So, and now we will go to range quanta and Doppler sampling. Imagine that this is one PRI, one pulse. But what I will do it after I receive pulse? Sampling. So once, like one PRI, it is sampled. Do you agree? So this is one PRI, this is second PRI, this is third PRI, and so on and so on and so on. Number of PRI that I will integrate together. Okay. If I will take one sample, it is this one. Second, this one, and so on and so on. From second PRI, first sample is this one, and this one, and this one. And what do you need to compute? Spectrum of signal. Do you agree? We are very dependent on spectrum. But how you won't compute spectrum from one sample, if you get my point? It is not possible. From this, it is also one sample. It is not possible. So imagine that there is visualization of what's happened. I will take example 1000 samples from PRI, put it there. 1000, put it there, and so on. Is it clear? Of course, it is. This not happen in reality, because you will continue. You want to compute spectrum. So you will take 1000 PRI, and we call it CPI. It is coherent processal interval. So from one PRI you can't compute spectrum. Why? You have one sample. How will look slow spectrum? One line or just one point? It is nothing. What do you need? You need more samples, of course, to compute spectrum. And it is this, we call it pulse compression. And now imagine I will take samples from first PRI, second, and so on, and make matrix. And then take it. This sample, always first sample for individual PRI. And if it will be 1000, then one CPI is 1000 of PRIs. And make matrix. So this is correspond of first sample of first PRIs, first sample of second PRI, and so on and so on and so on. And then I will always take this column, and how many values will be there if it's 1000 PRIs, 1000 samples, and can compute by FFT spectrum. And it is called Doppler filtering, and show you spectrum of your this one. This will be spectrum of second samples, and so on and so on. So it is mean this is spectrum in one time instance, second instance, spectrogram. But this not happen in reality because you will have continuous sample. But always, if you want to compute this spectrum, you need to wait for length of CPI, if you understand me. And I think that for today it was the hardest point. If you get this, it is perfect. Because, or if you have questions, just ask me. And of course, this length is one sampling interval. This we call it fast time. Why fast time? It is very fast. And this we call it slow time. So we have two times because you always waiting one PRI and one PRI and one PRI for corresponding samples. So please, we have two times slow and fast time. Fast time, samples in PRI, slow time, spectrum, like this one. And so if CPI will be only 100 samples, how will look your spectrum? Not much good. Why? Because you have only 100 samples, so it will be not so many information. So if you will have higher, longer CPI, you will get better resolution on spectrum. And better resolution, you can easily more separate targets. But yeah. Of course, but please be careful. You need also make a higher level of sampling. So this is little confusing because it is like sampling in time and number of CPI. It is like sampling in slow time, if you get my point. So it is little confusing. Now I will talk something about pulse compression. I already show rectangular pulse without any modulation. Autocorrelation function is triangle. Yes. If I will make cross correlation with receiving pulse, it will be in spectrum is sine x divided x since function. So wall energy triangle has very pure very pure resolution because it is triangle. It is really not narrow. You can agree with me. Spectrum of this is since function. It is also clear. And now, what is pulse compression? Pulse compression is that I want same energy which is in a rectangular pulse, put it to another pulse that has much narrow main lobe. Why? Because then I can recognize, then I have better resolution. So this is called pulse compression, and there is example of LFM compression linear frequency modulation. So the basic motivation is to decouple peak power from range resolution. Classic short rectangular pulse give good resolution, but to reach long range we would need very high power. But I don't have this power, or I can't even make this so high power. So I need reducing, and I will use inner modulation. So with pulse compression you can transmit long low peak pulse with intrapulse modulation. So energy will be same and pulse will be long enough. Because how you can in spectrum if you have sinus function, it is clear that main lobe is inverse value of pulse length. But I can make 1 nanosecond, 0.1 nanoseconds. You can't do it because it is so short. So pulse compression allows me make longer pulse but with the same resolution. So it is my motivation. I will skip international mismatch filter. I'm sorry, something happened. Okay. Which radar signal we use for for radar signals? It is unmodulated signal. Okay, it is rectangular pulse. Then we use linear frequency modulation, LFM. Non-linear frequency modulation, it is NLFM. Frequency keying and phase modulations. So BPSK, MFPSK, QPSK, Barker codes, minimum peak cyclope, pseudo-random sequences, code approximation, peak codes, Frank codes, and so many others. Guys, this is just definition what is inside the pulse. And each this signal has own unique properties, generally. Then MTI filtration. MTI filtration, I already told you, it is removing of clutter. So ground clutter suppression is on MTI. Then there is example of MTI filters. There is two targets, if you can recognize, and this is jamming. So it is some chaff jamming. I don't know if you know what is chaff jamming. It is, imagine that you have somebody want to track you, or some missiles goes to your site and want to hit you. And you will see which kind of missile, and you will just send to air cloud of small metallic plates or something like this, and size of this metallic small plates that flow in wind, they have like half of wavelength of this your frequency, and for missile will be like, oh, where is target, because they didn't see you after this cloud. So it is chaff. It is small, it is millions of small metallic, some not plates, it is like aluminium, something like this. If you get my point, it is something like this. This is clutter. There you can see it is after MTD, it is MTI filter. So this is no moving, so it is chaff, probably no wind because there is chaff. This jamming, you can saw it in MTI, after MTI MTD in zero Doppler shift. So it is mean there is no movement of this chaff, so you can see it there. And this is output from MTD filter, and I don't know in which speed, I am sorry, but imagine this is the whole picture. What is target? I don't know. I see everything. I see reflection from chaff, I see reflection from environment, I see some screen, this one. After I check MTI, there I see only static object, what is not movement. Chaff, environment, clear. And after MTD, I see only what is movement. Same source data, different filtration. It is like selection, what do you want to see, generally. And there I have nice picture, this of MTD. Check it, this is MTD filter. There you can see this value. It is minus 23.3 meter per second. So it is negative, it is, these targets go away from you, from radar, or opposite side. And check it, I will do it multiple times. Check the speed, you see different and different and different. Okay, there was speed 0, clutter, environment. Okay, I will do it again. I don't want to make animation because if we need to stop somewhere, so. And this is real data from radar. I can't tell from which one, but it is from radar. Okay, then next steps in radar signal processing is detection. Detection is evaluation of target's presence in a resolution cell. It is target there or it is not there. So it is statistics, you will like it. So it is two like hypotheses. Null hypothesis, noise only hypothesis, target is not present in cell. Alternative hypothesis, H1, target, echo, and noise is present because noise is always there. So target, no target. Then type 1 error is that we decide target is present, but it is not true. You understand me? Because, okay, I evaluate due to noise, okay, amplitude was higher in my resolution cell, and I decide, yes, there is target, but it is not true. But of course, I don't know it. It is statistics. Then second type of error is that there is target in my cell. Sorry, I decided there is no target, but it is not true. Target is there in my cell. And the detection or detector always need to make this decision of hypothesis. And it is depends, of course, on probability of false alarm and and inversion value 1 minus PD is that I miss target. So it is probability of false alarm because I decide, okay, there is target, but it is not true. And there I tell there is only noise, but it is target. So somebody can tell me, okay, if I don't want to miss anything, I will set probability of false alarm very, very low, because then I will detect almost everything. But you will have so many false detection, if you get my point, because I tell, okay, if I will threshold will be low, then I tell, okay, it is low. So any noise disturbance, any some higher amplitude, something told me there is target, there is target, there is target, and it is not true. And what's happened? On your screen you will see so many targets, and then it it is not true. If I will set opposite, so detectability rate very, how to say, high, then I can miss weak target. Why? Because it is I expecting so high amplitude, but unfortunately this is weak target, so low reflection. So we need you also with statistic. And this is a little like crystal ball, it is not easy to compute. And of course, it is depends on also CFAR, constant false alarm rate, because this CFAR told you what is false alarm rate, what is probability, and it is adaptive. If you see incoming storm with snowing something, your clutter for sure will increase, because it is clear, because there will be more reflection, so you will increase this threshold or decrease and so on. So it is usually adaptive. Okay, I will skip this. Then is extraction. Next one step is extraction of target coordinates. It is consolidation of target information gained from multiple observation. It is through CPI, because I told you we have PRI and we send these pulses. We make sampling, we gather all information from all pulses, and then we need make fitting which target correspond to same, which pulses correspond to same target. It is one big target, it is two small targets that as fly close to each other, and so on and so on. And in these steps I make determination of target coordinates, and then next step is classification of target, and it is mean classification is determination of targets class. It is fixed wing, helicopter, or it is wind turbines. What is it? And I can recognize from amount of information what I have. Adaptive CFAR, I will integration, it is utilization of more echoes received upon illumination of one target. If I have one illumination, if I have more illumination, I need to put together. There you have approximate values that is used for non-fluctuating and fluctuating targets. So detection probability is 0.9, false alarm rate is 10⁻⁶, for fluctuating is usually 0.n and again 10⁻⁶, so it is just like typical values. Okay, and I talk about classification. Yes, okay. Sorry for speed up a little, but this rest is not so affect other lectures. Slow, fast time, it is important for us, but after this it is like secondary processing and then tertiary processing, but it is we will not be affected for next lecture. So I don't know what is time. Okay, okay. So we are missing tutorial today, but I will start tomorrow not with lecture 3 but with tutorial. Please take your laptop, and I will ask if you could send me all participant emails, or I will ask organizer if they can send me a list of emails, and I will send you all material. I will send you link where you can download all these MATLAB files, and tomorrow morning you will receive email, and please take your laptop as possible, and we will work all together on this tutorial. Thank you for your attention, and that you have patience with 5 hours with me.
Today's session is over. We will meet tomorrow at 10.